इसलिए तो करेंगे क्योंकि
आपका फर्स्ट सेकंड ईयर है?
नमस्ते सर।
नमस्ते जी, आई कांट हियर यू, थोड़ा वॉल्यूम तेज होगा।
जी सर, नमस्ते सर। अभी सर आवाज।
गुड मॉर्निंग।
गुड मॉर्निंग।
आई एम जस्ट चेकिंग द कनेक्शंस, तो थोड़ा तेज कर दो, वॉल्यूम हो सकता है।
जी सर।
मेरा तो वॉल्यूम
तो फुल है सर।
मेरा भी फुल है यार, आई डोंट नो व्हाई। कैन यू हियर मी क्लियरली?
या, यू आर कंप्लीटली ऑडिबल सर।
Okay, then I think that's okay. Let me see if I can. How about the camera?
Your camera is good sir. You're.
Pardon?
Yes sir, you're completely audible and visible.
Okay, fine. So is this setting okay?
Good morning, sir.
Good morning, ma'am. How are you?
I'm fine, sir. How are you, sir?
Absolutely fine. Great. I just trying to set the connections and other things.
Yes, sir. Yes, sir. You are
I was
visible.
away for almost 2.5 months and I returned yesterday.
Yeah.
अभी ठीक है मेरा सब?
Yes, sir. Yes, sir.
Should I leave it as such?
Yes, sir.
Yeah.
Good morning, sir.
कुछ change हुआ तो बोलना.
Sir, your camera is
Not really good.
no, yes sir, exactly, not really good. You should little bit move your camera.
Move towards what? Front, back, left, right?
Upper side sir.
Upper side.
Yes, your face is not complete. Yeah,
Like this?
that's good. Yeah. Yes sir, it's good.
Okay. I'll put something. Just a minute. Let me put some book. Is it okay now?
Yes sir.
Tiwari sir, namaste, sir.
Sir,
Namaste,
not really
kaise
good.
ma'am?
Little bit.
Namaste, sir. Namaste, sir.
Up sir, upper side. Now sir, now okay. Yes sir, now it's okay. Yes.
Is it okay? Is it okay now?
Yes sir.
I have another camera. If you want, I can show that. I don't know.
Yes sir, it's completely okay.
Fine?
Yes sir, fine.
All right. I have to reorganize many things suddenly. So many wires, sir. Can you remove these wires? Why don't you put it in the next one? इधर वाले लगाओ। अच्छा वहाँ रखो।
हाँ आप ज्वाइन हो। सर नमस्ते सर।
Namaste, sir.
एक मिनट बोलो। आवाज नहीं है। ठीक 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 अनम्यूट किया। सर नमस्ते। आवाज क्लियर नहीं।
Good morning, sir. Good morning.
सर नमस्कार सर।
मैडम
नमस्ते
नमस्कार।
मैडम नमस्ते।
नमस्ते अजय, नमस्कार, गुड मॉर्निंग।
मैडम नमस्ते।
नमस्ते। चलो अभी तो अच्छा लग रहा है, काफी लोग जुड़ते जा रहे हैं, थोड़ा जल्दी जुड़ रहे हैं, ये अच्छी बात है।
जी जी नहीं सभी लोग, तिवारी सर भी आ गए, किसी सर भी आ गए थे, प्रिंसिपल साहब भी आ गए,
हाँ।
मैडम भी है, तो मुझे लगता है प्रोग्राम शुरू करवाएंगे।
बिल्कुल टाइमली हो जाएगा शुरू।
जी 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 जी।
सर नमस्कार। सर नमस्कार।
मैडम भी आ गई हैं। प्रिंसिपल साहब
क्या अभी टाइम है अपने पास? 10 मिनट और हैं अभी।
हाँ 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 program will be started at 11 o'clock sharp, so please join us with us.
Yes, sir. I'll circulate the message.
Okay. भावना मानसी है?
Yes, ma'am. Yes, sir.
Okay, okay, okay. So after 5 minutes we will start.
Okay, sir.
सर नमस्कार.
सर नमस्कार. गुड मॉर्निंग सर. गुड मॉर्निंग.
जय हिंद सर. जय हिंद. नमस्ते सर.
बेटा वो गाड़ी के पीछे ठू होगा, पॉलिथीन होगा, वो लिया निकाल के पीछे वाले सीट पर. हाँ सर. है क्या? कहाँ पर? कहाँ से? चलो सर, वही मैं देख रहा था, हमको तो आइडिया है नहीं हमारे पास। सर ये रख लीजिएगा।
जुगल सर नमस्कार।
सर नमस्कार, गुड मॉर्निंग, हाउ आर यू?
फाइन फाइन सर,
Namaskar,
फाइन।
sir.
नमस्कार मैडम, नमस्कार।
Morning, sir. Morning, ma'am.
Morning.
Bhavna,
Yes, sir.
I think,
Shall we start?
yeah.
Yes, sir.
सर लोग हैं इसमें। एक मिनट, जस्ट वेट।
थोड़ा सा वेट कर लो, अभी 2-3 मिनट है।
हाँ हाँ,
Sir, shall we start?
जस्ट वेट 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 वेट।
Okay.
अमित मान से AK सिंह सर है?
है।
तो फिर स्टार्ट किया जाए फिर। एक मिनट जस्ट।
अजय स्टार्ट करें।
हाँ
हाँ, मानसी प्लीज स्टार्ट।
मानसी, म्यूट, अनम्यूट योरसेल्फ।
Yes, sir. Good morning, everyone. I'm highly pleased welcoming you all to international webinar on recent trends in science and technology from 20th December 2021 to 22nd December 2021, organized by Department of Chemistry, Government VYT PG Autonomous College, Durg, in association with Siddhachalam Laboratory, Raipur, Chhattisgarh. On behalf of the organizing committee, I, Mansi Yadu, welcome you all for your presence and contribution in the webinar. The organizing committee welcomes today's chief guest, Professor Anil Kumar Singh, Director, Rashtriya Chemicals and Fertilizers Limited, Mumbai, and guest of honor, Dr. Sushil Chandra Tiwari, sir, Additional Director, Department of Higher Education, Durg Zone, and all other respected guests and participants between us. With this, I invite Dr. Bhavna Jain, Principal Scientist, Siddhachalam Laboratory, to begin with the event. Ma'am, please.
Thank you, Mansi. Welcome, Honorable Chief Guest, Dr. A.K. Singh, Rashtriya, Director, Rashtriya Chemicals and Fertilizer Limited, Mumbai, India. Today's guest of honor, Dr. Sushil Chandra Tiwari, Additional Director, Department of Higher Education, Durg Zone, Principal Dr. R.N. Singh, and all other respected guests and dignitaries. It is my pleasure to introduce all the eminent dignitaries to today's webinar that have joined us across the country to share their knowledge and enhance your research skill. At last, I sincerely hope all the participants and everyone will enjoy today's session and next 3-day session, as well as they will learn new things, definitely. Thank you so much.
Thank you, ma'am. Now, I invite Dr. A.K. Singh, sir, from Department of Chemistry, Government VYT PG Autonomous College, Durg, to begin with this event.
Thank you, Mansi. Good morning to all dignitaries and participants. In the capacity of Organizing Secretary of the webinar, I extend my heartiest welcome to all dignitaries. It is a matter of great pleasure and honor to host this international webinar on recent trends in science and technology in collaboration with the Siddhachalam Laboratory, Raipur. You will be happy to know that nearly 300 participants from 6 countries and 18 states of India are participating in this webinar in various capacities. Global health is facing the most dangerous situation regarding the novel severe acute respiratory syndrome called coronavirus 2, which is widely known as COVID-19 pandemic. This is due to the highly infectious nature of the disease. Science and technology can significantly address the many clinical and public healthcare challenges that have arisen from the coronavirus pandemic. It can help in the fight against this pandemic disease and ongoing mitigation strategies. Nano-based functional materials are currently being developed and deployed for the containment, diagnosis, and treatment of COVID-19. Science and technology approaches show how these disciplines can help the medicinal, technical, and scientific communities to fight the pandemic, highlighting the development of functional nanomaterials for detection, sanitation, therapies, and vaccines for the betterment of the society. I am indebted to our chief guest, Professor Anil Kumar Singh, Director, Rashtriya Chemical Fertilizer Limited, Mumbai, for his support and continuous encouragement. He is a person who has been the source of inspiration for organizing such webinar. Sir, please accept my sincere thanks. After annual session, we have a technical session in which we will be listening to 2 distinguished scientists, Professor Srikant D. Junalgadda, University of KwaZulu-Natal, South Africa, Professor Muhammad Abu bin Hassan Susan, Dhaka University, Bangladesh. And after invited talk, we have oral presentation of 13 students. And on the second day, we have 3 distinguished speakers, Professor Rameswar Adhikari, Nepal, from Nepal, Dr. Ashish, Central Center for Display Technology, IIT Kanpur, and Dr. Sunita Samaria from Government College, Chhattisgarh. After invited talk, we have oral presentation of 13 students. On the third day, we have 2 distinguished speakers, Dr. Surprakash Singh, IICT Hyderabad, and Dr. Rajesh Pandit from Nepal. After invited talk, we have 6 to 8 poster presentations. Each presentation, either oral or presentation or poster, will be evaluated by eminent jury members. An Young Scientist Award and Best Presentation Award will be given to winner of the participant. After each lecture and presentation, the session will be open for discussion and question answers. I am confident that the participants will use this opportunity and enhance their knowledge. Thank you very much.
Thank you, sir. Now I invite Professor Irtst Tiwari from Department of Chemistry, Government VYT PG Autonomous College, Durg, for welcome address.
Good morning, everyone. Honorable Chief Guest, Dr. A.K. Singh, Director, Rashtriya Chemicals and Fertilizers Limited, Mumbai. Guest of Honor, Dr. S.C. Tiwari, Additional Director, Department of Higher Education, Durg Zone. Patron, Dr. R.N. Singh, Principal, Government VYT Autonomous PG College, Durg. Head of the Chemistry Department, Dr. Anupma Asthana. All professors and research scholars. A very warm welcome to all the renowned speakers and delegates who took out their valuable time and joined us today to be the part of this international conference organized by the Chemistry Department of Government VYT Autonomous PG College, Durg, in association with Siddhachalam Laboratory, Raipur, Chhattisgarh. We are honored to have you all with us. The goal of this conference is to exchange the fundamental knowledge of chemistry between the eminent scientists and researchers. It will also provide an international platform for researchers. It will, and to discuss the most recent innovations, trends, practical challenges, and the solutions adopted in the field of chemical sciences. We are delighted to extend our warm welcome to the dignitaries from South Africa, Bangladesh, Nepal, IIT Kanpur, India, who will be sharing their knowledge with us for our mutual benefits. I once again welcome honorable guests with the request to permit us to proceed with our conference. Thank you very much.
Thank you, ma'am. Now I invite Professor Anupama Asthana, ma'am, Head of the Chemistry Department, Government VYT PG Autonomous College, Durg, for her address.
Good morning, everybody. Guest of this webinar, respected Professor Anil Kumar Singh, Director, Rashtriya Chemicals and Fertilizers Limited, Mumbai. Our guest of honor, Dr. Sushil Chand Tiwari, Additional Director, Department of Higher Education, Durg Zone, Chhattisgarh. Dr. R.N. Singh, Principal of our Institute, and Patron Dr. Bhavna Jain, Principal Scientist, Siddhachalam Laboratory, Raipur. Convener of the program, Dr. Irtst Tiwari. Organizing Secretary, Dr. Ajay Kumar Singh. Joint Secretary, Dr. Sunita Matthew. Respected eminent speakers from India and abroad, all faculty members, research scholars, and dear students. I, on behalf of my institute, welcome you all to this inaugural session on recent trends on science and technology. I am grateful to Dr. A. Singh for sparing his valuable time and kindly accepting our invitation for this virtual conference. I am thankful to him for his guidance and unconditional support. Being an expert in this field, we understand, sir, how difficult it is for you to give us so much time and concern. Thank you very much, sir. I am thankful to Dr. Sushil Chand Tiwari, sir, for his support and time-to-time guidance. Science and technology today has become an integral part of our environment. We are living it. And over the period, we have reached a point where we can't survive without the use of science and technology in our daily life. Be it the field of medical, industrial, communication, or transportation, or our kitchen, or our lifestyle. we don't find a single place around us where we don't find use of science and technology. Researchers, scientists of biological science, medical science, physical science, material science, and various technological faculties have come forward and worked together. This is the need of hour. In the recent times, we have seen how science and technology came to our rescue during the difficult pandemic situation, where our scientists, researchers, all engineers worked together. They were working jointly, developed vaccines, medicines, and virtual means of communication were adopted worldwide. Artificial intelligence is in recent times, in recent scenario, has become one of the most commonly used technology with various applications worldwide. Here participants, field of science and technology is so fast now that it is very difficult to work in isolation. This calls for more and more collaborative joint work and joint ventures, and such national and international conferences or seminars, workshops give us opportunity for such collaborations, and this is the need of society for better development. Dear researchers, I would like to inform you, young minds, I would like to inform you that Dr. Bhavna Jain has taken a good initiative. Our student from this college has taken a good initiative and is set a very good research lab in the field of this research, advanced research in the field of chemical sciences. I congratulate you, Bhavna, and I request all young minds, the young researchers, to take this opportunity to interact with all international national speakers over the 3 days and give your presentations. I once again extend my sincere thanks to all dignitaries who are here to witness this conference. Thank you once again. Thank you very much.
Thank you so much, ma'am. Now, today we are highly pleased by the presence of Dr. R.N. Singh, Principal, Government VYT PG Autonomous College, Durg, between us. Now I request Dr. Singh to guide us with his words.
Very good morning to all dignitaries, participants, and members of organizing committee. I extend warm welcome to your chief guest of today functions, Professor A.K. Singh from Rashtriya Chemical and Fertilizer Limited, Mumbai. Guest of honor, Dr. Sushil Chand Tiwari, Addition Director. Our guest speaker, Professor S.D. Jonalagunda, South Africa. Professor Mohammad Abu bin Hussain from Bangladesh. Professor Rameshwar Adhikari from Nepal. Dr. Ashish from Kanpur. Dr. Sunita Sonwaria from Surajpur. Surya Prakash Singh from Hyderabad. And Professor Rajesh Pandit from Nepal. I also welcome to all participants from different parts of country for your participation and contribution in present international webinar on recent trends in science and technology, which is jointly organized by the Department of Chemistry of our college and Siddhachalam Laboratory, Raipur. Dear friends, as I feel that the topic of this webinar is very relevant because of emerging challenges on human and environment. Recently, we are facing several problems like pandemic, climate, population, shortage of foods, regulation of geochemical cycle, shortage of energy, water, and interruption in solar emissions. So today, we are bound to explore science and only science to save Earth and life in Earth, and this is possible only through scientific debates. That's why the present webinar is very relevant. I hope that present gathering will conclude some point to fill fulfill the objectives. I extend a special thanks to organizing department as well as Dr. Bhavna Jain of our collaborative partners of this webinar. I also appreciate all members who are contributing in this webinar. Thank you. Thank you very much.
Thank you, sir. Now, I request Dr. Anupama Asthana, ma'am, to formally introduce our guest of honor, Dr. Sushil Chandra Tiwari, sir.
Today, I take this opportunity to introduce Professor Sushil Chandra Tiwari, sir. Presently, he is working as Additional Director, Higher Education, Chhattisgarh State, Durg Division. Dr. Tiwari has vast teaching experience and he is very good in academics and working and serving this state, our state, in various capacities. To name a few, he is member of Chairman Board of Studies, Government Digvijay Autonomous College, Rajangaon, member IQAC, Government Digvijay Autonomous College, Rajangaon, member Executive Council, Pandit Ravi Shankar Shukla University, Raipur, member Vidya Parishad, Pandit Ravi Shankar Shukla University, Raipur, member Governing Body, Kalyan PG College, Bhilai Nagar, member Academic Council, Hemchand Yadav University, Durg, member Governing Body, ITM University, Raipur, member of various autonomous extension and grants committee, member Vice Chancellor selection committees in various in various universities, member State NEC and Autonomous Monitoring Cell, and member of various academic and confidential work. With due respect, I welcome you, sir, and I invite for your kind words. Sir?
Yes.
Thank you, sir. Thank you.
Respected dignitaries, academicians, researchers, and the organizers of this prestigious webinar, it gives me immense pleasure to note that such a great online event is being organized by the most prestigious college of our state. It gives a platform to young researchers to present their work, and it is an opportunity for experts to evaluate and provide their suggestions for improvement. It is highly appreciable that a reputed laboratories from private sector is also involved in this webinar. This shows the participation of industry and academia in the field of research is being taken up very sincerely as per the suggestions of our policy makers like University Grant Commission and National Education Policy. I wish all the best for a great interchange of ideas and research outcomes. I would especially like to praise the effort of Principal Dr. R.N. Singh and the excellent professors in the Department of Chemistry for organizing such a great event. Thank you and wish you all the best. Thanks.
Thank you so much, sir. Now, I request Dr. Ajay Singh, sir, to formally welcome our chief guest, Professor Anil Kumar Singh, sir.
I think I am
Sir, you are muted.
Okay. Sorry.
Ajay Singh, sir,
Okay.
you are
Yeah.
muted. Please unmute
Yes.
yourself.
Yes. I think I am unmuted.
Yes, sir. Now you are
Yeah.
audible.
Okay. Sorry. Professor Anil Kumar Singh earned PhD in 1978 from IIT Kanpur. After postdoctoral stints at Florida State University, USA, University of Hawaii at Manoa, USA, and Columbia University in the city of New York, he returned to India in 1982 to join University of Roorkee as lecturer in chemistry. In January 1983, he moved to IIT Bombay as lecturer in chemistry, where he subsequently rose to the rank of full professor in 1990. During 1989, he was visiting scientist in the Department of Chemistry, University of Montreal, Canada. He has briefly also worked at Syracuse University in New York. He superannuated from in IIT Bombay in April 2017 as professor in the highest academic grade scale. Subsequently, he was re-employed by IIT Bombay as HAG professor and served there till June 30, 2017. Currently, Professor Singh is a director independent of Rashtriya Chemicals and Fertilizer Limited, Mumbai, a PSU of Government of India, Ministry of Chemicals and Fertilizers. He is also adjunct professor at the Institute of Chemical Technology, Mumbai, Category 1, deemed to be University, MHRD, and UGC, and Elite Status Center of Excellence, Government of Maharashtra. He is also an honorary visiting professor at the B.K. Birla College, Kalyan, Thane. He is also chairman of Mumbai chapter of National Academy of Sciences, India. There is a long list of Professor Singh. So I would like to invite Professor Singh to say something about our conference. Professor Singh. Sir, AK Singh, sir, please unmute your. So. Yeah.
Can you hear me now?
Yeah, fine, sir.
Okay. So thank you very much, Dr. Singh, and a very good morning to all of you attending this event. Our guest of honor, Additional Director, Department of Higher Education, Durg Zone, Chhattisgarh, Dr. Sushil Chand Tiwari ji. Patrons of this event, Principal Aryan Singh, and Principal Scientist of Siddharthalam Laboratory, Raipur, Dr. Bhavna Jain. Distinguished invitees and academicians from India and abroad. Chairperson of the event and Head of Chemistry Department of the college, Madam Professor Anupama Asthana ji. Convener of this webinar, Madam Professor Alka Tiwari ji. Organizing Secretary, Professor Ajay Kumar Singh ji. Joint Secretary, Dr. Sunita Matthew ji. Members of Organizing Committee, learned faculty members, officers and staff members of BYT PG College, dear students, participants, esteemed media personnel, if any, friends and family, ladies and gentlemen. I feel very privileged to address to you in this international webinar, and I sincerely thank the organizers for this opportunity. I'm also very happy to see the resolve of this college to establish ceremony with the rest of the world, including society and industry. It is satisfying to know that by dint of sheer unflagging commitment to excellence made by various stakeholders, this college is fast marching on the path of progress, yielding rich scholastic dividends. So the VYT family, you have every reason to be filled with a sense of pride and fulfillment. And I extend my heartfelt congratulations and felicitations for your successes. Now, coming to this technical aspect of the webinar, I note that you have planned to uncover several important areas, including material science, green chemistry, agrochemistry, wastewater treatment, advanced oxidation processes, bioinorganic chemistry, polymer science, catalysis, coordination and organometallic chemistry, photochemistry, organic sciences, supramolecular systems, also including biotech, microbiology, and sustainable environment, etc. All these areas have great bearing on many sectors of our concern, be it agriculture, energy, environment, food and nutrition, health, ocean and space, manufacturing, and also, very importantly, managing and imparting quality education in science and technology. Many challenges and opportunities lie ahead of us. All of you are aware of this. The COVID pandemic has brought further new challenges and opportunities for new activities in science and technology education and research and development, leading to the development of appropriate technologies. If you look at only a few of these opportunities, you will be amazed to see how these would be positively impacting our way of practicing science and technology education, research and development. With regard to the changing scenario in education, we must remember that emerging technologies demand much of multidimensional knowledge, cooperation, and collaboration. And all this depends much on the cadre of intelligent and superbly trained students who will be able to generate new scientific knowledge and further take that scientific knowledge to higher levels of technologies and appropriate technologies. Since universities and colleges are the principal focus of science and technology education and research, and that it is here new knowledge is generated and created, these institutions have to take steps to meet the new challenges through their academic and research programs. They need to redesign and continuously upgrade curricular structure, course content, and most importantly, the delivery of the course content in terms of skills necessary for coping with demands of today's requirement and in general, the demands of the 21st century. In this context, our graduates must be prepared for multicultural and multilinguistic workplace settings. It is important that students are exposed to a wide variety of disciplines and encouraged to develop the capacity to see the world from multiple perspectives. Another point of concern is the need for finding the missing links that foster meaningful academia-industry cooperation for improving education and development of appropriate technologies, and hence the employment. As you know, innovation arises from academic and industrial research, but industrial research plays a crucial role in ensuring that innovations are practical and profitable. Industrial scientists and technologists do need encouragement and appreciation of academicians. We need to change our ways of looking at each other and do all that is necessary to bridge the gap that exists between two. I'm very happy that this webinar is organized in association with Siddhachalam Laboratory, which I understand is an industry committed to the development of science research skills, particularly in chemical analytical area, water and soil testing, etc., by offering quality services and analysis as per international standards. It is satisfying to note that this lab, equipped with modern facilities, is interfacing with academic institutions like your college and helping science students interested in advanced science and technology. Ladies and gentlemen, let's remember that basic research in science and technology by definition is motivated purely by curiosity and the quest of knowledge, more than often without a clear, practical, and commercial objectives. Yet, basic research is the source from which all commercially oriented applied research and development ultimately flows. In fact, the commercial potential of a particular basic discovery is often unanticipated. Also, quite often, such discoveries extend to many economically unrelated industries and applications and to the larger benefit of society in the long run. There are abundant examples of university and college-based research that has yielded enormous and unprecedented, unanticipated benefits. Let me just share one or two examples of this. You know, discovery of lasers is one such example. As you know, Professor William Bennett started working on the phenomenon of coherent light in the 1950s, and his research was mainly funded by the government agencies. For many years, the laser was what Professor Bennett called a solution looking for a problem. Today, as you know, there are numerous users for lasers. Lasers are used in situations as varied as cutting clothes, laying out a foundation of a house, making microchips, defense and space technology, healthcare, for instance, in pinpointing and treating brain tumors, for example, that too without any surgery. In fact, when Professor Bennett suffered a detached retina in 1995, the treatment he received at the Yale University was accomplished by using precisely the same organ laser that Professor Bennett developed at Yale University in the year 1964. So you can just imagine something which was discovered long, long ago came to use much later. Another example of unprecedented emerging technological dimension is that of the biological photoreceptors involved in energy and sensory transductions. An example of this is our vision process itself, which is nothing but a biomolecular technology evolved by the nature. While fundamental science like physics, chemistry, biology, etc., have provided us the basic understanding of this process, the engineers and technologists have taken that scientific knowledge to develop a number of very high-end technologies and very useful in development of numerous devices for various applications such as optical information processing tools, holographic thin films, memory devices, optical computing, and vision-related defense and medical devices, etc. In fact, quest for finding novel functional optical systems similar to the vision system has taken researchers to find bacterial photoreceptors. And such bacterial photoreceptors have also been used as optical material in various technologies. And in fact, they are trying to replace those made out of semiconductor-based technologies, just for example, used in associated memory devices. Yet another example that comes to my mind is the recent most discovery, very recent most discovery of an emerging
Sir, you are muted. Anil sir? Singh sir, you are muted. Yes, sir. Thank you, sir.
Another thing that I want to bring to your kind attention is the repurposing of carbon dioxide for the production of fuels and platform chemicals, which is very important in today's time with respect to environment and energy. And in this context, I think production of economically and environmentally viable catalytic system is of great importance. Anyway, I think I have to curtail my address, and let me just take another a few minutes to tell you what is happening very, very recently. And I think all scientists, chemists, physicists, biologists should take note of it and try to develop the subject more. For example, quantum computing. I will not go in detail. I'll only read the names of these topics. Quantum computing is very, very important and something need to be done in this country and elsewhere as well. 3D printing for bioorgans, that is three-dimensional bioprinting, is a state-of-the-art technology and science that is needed in the medical sciences. Synthetic biology, that is redesigning organisms for useful purpose by engineering them to have new abilities, very important. Full genome sequencing, I don't have to tell you why it is very important in COVID time. That is very, very important. It is coming up. Synthetic meat, that is in vitro cell cultures of animal cells. Those who are in life science and microbiology should take note of it. Similarly, solutions for climate change. I talked about changing our main energy sources to clean and renewable energy using carbon dioxide. Extreme materials. I think your college is very much involved in this. We need to develop multifunctional materials which can be used in extreme conditions of temperature, pressure, oxidation, radiation, etc. Digital chemical synthesis, very, very new and upcoming area where robot chemists are being developed to do the organic synthesis, which otherwise is done by using manpower and is very environmentally unfriendly. Then aquaporin membranes for desalination process. And one can think of making aquaporin biomimetic membranes for the purpose. Hydrate desalination, those who are in chemistry, they should look into this, how to develop hydrates for desalination of sea, water, etc. That is very, very important and it's coming up. Then we have tissue engineering, a very important area today, which basically seeks to repair, replace, or regenerate tissues or organs by translating fundamental knowledge of physics, chemistry, and biology. Regenerative medicine, again a branch of medicine and biology that develops methods to regrow and repair and replace damaged or diseased cells. Systems biology, those who are in geology, for example, they should look into this. Basically, it is computational and mathematical analysis of modeling of complex biological systems. Smart drug delivery, related to therapeutic approach to deliver drugs to a desired site in desired dose and target. Artificial intelligence, somebody has talked about. There are so many areas. So I think, and finally, but not least important, very, very important is science for circular economy, a new upcoming area, circular economy based science, which is energy and materials resources are used in circles to optimize production and minimize inputs, etc. So finally, ladies and gentlemen, I'm sorry I have taken a few more minutes, but I thought it is very important to bring to your attention as to what is happening globally in science and technology, particularly chemistry, physics, and biology, because we are all academic institutions and we need to take note of these things to develop and do new things. I'm very happy that your college has organized this webinar, and I hope that the lectures and various presentations made would go a long way in defining, designing, and delivering education, research, and development programs in areas of your concern. I hope that deliberations made would sensitize and catalyze many towards multi and cross-disciplinary endeavors and an approach of wholeness rather than that of segregation and compartmentalization. I hope that suitable recommendations would emerge to improve upon education and research in science and technology and also enhance efficient and meaningful engagement with the industry. With this, I conclude and once again convey my warm greetings, felicitations, and best wishes for grand success of this webinar. I wish you all resounding success in your future endeavors and fulfillment of your cherished ideals and goals. May the deliberations of this webinar instill in all hope and determination to venture into what remains hitherto unexplored in science and technology. Thank you very much. Thank you all for your patient hearing. Thanks a lot. Over to you, please.
Thank you so much, sir. Now, heading towards the end of this inaugural session, I invite Dr. Sunita B. Matthew ma'am from Department of Chemistry of Government VYT PG Autonomous College Durg to propose a formal vote of thanks.
Thank you, Mansi. Honorable and respected virtual dais and all dear participants, a warm greetings to you all. Indeed, we are very fortunate to have this morning very learned personalities on this virtual platform for this webinar. At the very outset, on behalf of our department and institution, I extend our heartfelt thanks to our chief guest, Professor Anil Kumar Singh, Chairman, NASI Mumbai chapter, for sparing his valuable time and for enlightening us with exemplary words of wisdom and for highlighting us of the various unexplored areas of research and the need for research aptitude, curiosity, and quest for better innovative research work. Thank you, sir. Our sincere thanks is due to Professor S.C. Tiwari, sir, Additional Director, Chhattisgarh Higher Education Department, and Principal, Government W.W. Patangar Girls College, Durg, for gracing the occasion and for the inspirational words. Thank you, sir, for all the encouragement and support which is always there with us. Thank you, sir, once again. Our patron and principal, Professor R.N. Singh, is our driving force and always motivates us to take such initiatives. Thank you, sir, for all the support and guidance. Now I take this opportunity to extend our sincere gratitude to all our invited speakers, chairpersons, and jury members in anticipation for accepting our invitation and for the benign presence. Thank you all. No program is successful without proper execution. I extend my thanks to the entire organizing team of our department and Siddhachalam Laboratory, especially Bhavna Jain, for taking this initiative and providing this virtual platform for interaction. Last but not the least, without participants, such events cannot be possible. Thank you all for being with us today. Once again, I extend my thanks to one and all for being on this virtual platform. Thank you. Over to you, Mansi.
Thank you so much, ma'am. After this successful inaugural session, now we shall move towards the technical session. This international webinar, organized by the Department of Chemistry in association with Siddhachalam Laboratory, Raipur, Chhattisgarh, will provide a common platform for experts, young scholars, and students to present their work, interact, and exchange their innovative ideas in the field of functional material, water treatment, engineering, agrochemistry, etc. Today, on the first day, we have Professor S.B. Jonanglaro sir from South Africa and Professor M.A.B.H. Sushant sir from Bangladesh with us. The organizing committee welcomes the dignitaries. There will be total 32 participants with oral and poster presentation, out of which 13 participants will present today. Now, I once again request Dr. Sunita Matthew ma'am to introduce our chairperson, Professor Ravin Manohar Jugade sir.
Thank you, Mansi. It's a great honor to introduce today's chairperson of the technical session to the audience. Professor Ravin Jugade is presently professor in analytical chemistry, RTM Nagpur University, Nagpur. His thrust area of research is electroanalytical chemistry, pharmaceutical analysis, water treatment using biopolymer materials. His research contribution is evident from his research publications. To his credit, there are 45 research publications, 12 textbooks, 4 articles in newspaper. His contribution is also evident from the research projects and the PhD awarded. Till now, 4 PhDs have been awarded and 8 scholars are working under his guidance. He is member of various academies. Apart from that, Professor Jugade has contributed to e-content development, and the lectures have been broadcasted on NPTEL and SOAM platforms. With this, I welcome you, sir, to the technical session and hand over the technical session to you, sir. Sir, please take over.
Thank you very much, Dr. Matthew. Thank you very much for the nice words of introduction and a brief introduction regarding the session. Now, as far as this session is concerned, it is divided into 3 parts. The first component, there will be a keynote speech by Professor Shrikanta Jonalgadda from South Africa, followed by another keynote speech by Professor Abu bin Hassan Susan from Bangladesh, and followed by the oral presentations by 12 researchers. To start with the session, I invite Professor Shrikanta Jonalgadda. Professor Shrikanta B. Jonalgadda has been a senior professor of chemistry at the University of KwaZulu-Natal since 2003. He is an elected fellow of University of KwaZulu-Natal, South Africa.
Can't hear.
Is with us.
Audio.
Hello. Singh sir, Ajay Singh sir.
Yeah. Am I audible?
Yeah,
Yes,
yeah.
sir, now you are audible.
I
Yes,
think
his research interest. Yeah, his
Yeah,
research
you-
interest include green chemistry, heterogeneous catalysis, value-added conversions, and water chemistry. So, with these words, I welcome Professor Jonalgadda for his keynote address. The time allotted is 30 minutes, followed by discussion in the form of question and answer for 5 minutes. Professor Jonalgadda, please.
Thank you. Can you see the screen?
No, sir.
Okay. Good morning, everybody. Can you see me? Can you see the slide?
No,
Hello?
sir.
No, it is not visible, sir.
Can you hear me?
Yeah,
Yes, sir.
yes, your voice is clear, but not visible your PPT or presentation.
Presentation, can you see my presentation?
No, sir.
No, sir.
Okay, just let me see what is happening. Is it okay now? Can you see me? Can you?
Sir, you will have to share your screen.
Huh?
You will have to share your screen.
I'm doing that, it is not. Okay.
Hello.
No, what you say?
Yeah.
Can
It
you
is
see
visible
me?
now.
It is visible now.
Yes, yes.
Okay, that's good. Thank you. Sorry for that inconvenience. Good morning. Today's my presentation. I'm going to talk about the nanocomposites and the novel materials. As catalysts for synthesis by multi-component synthesis. And this particular one. Okay, starting with the nanocomposites, as we know the nano, the term, that it shows us when you look at the size of the nano, take example, these days, we are nano is the very buzzword, and at the same time, the coronavirus. Coronavirus is, the nanovirus, as you can see that, but among the viruses, coronavirus is bigger one, but normal naked eye, we can see up to 40 micron size, 40 micron size for your idea. When you see when you are sitting in your room, light beam coming in the light beam, the particles moving like in the Brownian movement, those particles are of the size of about 40 microns. Once they are bigger than that, they won't float, they will settle down. Now, are you hearing me?
Yes, sir.
Okay. Sorry, what is happening? Okay. Now, prominence of nanotechnology. Nanotechnology is such a useful technology. Everywhere you see that, everywhere the applications of that, starting from the information technology, which is the best utilized, then the biotechnology or the environmental sciences, food science, and everywhere mechanical engineering and robotics, and everywhere we see the nanotechnology. When it comes to nanoparticles, while that is very good and useful, it is associated with it, there are problems. As I said, nanoparticles are, so small, normally our body systems can't stop them. That's one of the reasons we get exposed to nanoparticles and we get these infections. But one of the main things, very well-known, old-known example of the nanoparticles and the asbestos particles, normally affect the health and you get the cancer-like problems, but similarly, nanoparticles, when they enter your body system, your lungs, etc., they can cause many respiratory problems and other problems. That's why we have to be careful about, how we use our
I request the organizers to please mute all the others because some of the mics are on. I request all the organizers to mute all the others except the speaker. Yeah, okay, sir. You can go ahead.
Sorry for the discontinuity. Let me come back to the talk. Now the green chemistry is one of the new development starting from early 90s. It has come into place, and then it is so important. Green chemistry is designing the chemical products. Yes, as we know, without the chemistry we can't get anything, and everything is based on the chemistry. Whether it is the productive processes or the biological process, everything is related chemistry. Now, in this one, green chemistry is the one, to how we can eliminate the pollutants at the same time we get the benefits of the chemistry. That is the one utilization of the sets of the principles that based on the green principles. But the importance of that is, gained, the two Nobel Prizes in 2001 and 2005, both are green chemistry related principles. With that, green chemistry gained a lot of importance in the application aspect of it. Then what are the green principles? We see that the green principles are the 12 of them. You can see those 12 principles. All of you see also in our curriculum also it is taught. But what is important here, what I'm trying to, most of these green principles can be achieved using the catalyst. How we can achieve those, and I will show you in the next few slides. And catalysis is a very prime thing, and most of the industrial process, most of the processes are based on the catalysis, including all the petrochemical industry or the fine chemical industry. Everything is dependent on catalysis. Now, as we know how catalysis works, the same reaction, it provides an alternate pathway. That means, with a less amount of energy, as you can see a representation there, you have to go up the hill, and to go down is a more difficult process. Instead of that, if it is more or less very small energy is needed, you can roll it down with much easier way. That means, lesser the energy of activation, faster the reaction can be. When it comes to catalysis, we know homogeneous catalysis and heterogeneous catalysis are two types. Homogeneous means, everything in the same phase. Most of the times it's the liquid phase reactions we have happen to face, most of our laboratories, we do the
Sir, excuse me.
The other one is the heterogeneous catalysis. The heterogeneous catalysis has a great advantage. The thing is, it allows
Sir, excuse me. Your slides are not moving. I think your slides are not moving. It is still on slide number 4.
Oh. Is it now green chemistry? Can you see that?
No, sir. It's only slide number 4, diseases associated to nanoparticle exposure. That is only visible.
But why it is this? I didn't.
You can do one thing. You just unshare and again reshare it.
Okay. Is that okay?
Now it is slide number 4. Again, diseases
Okay, I will
associated.
try to change it. Okay. See now?
Yeah. Now it has been
Okay.
changed. Yes.
Okay, sorry for that. I don't know what is happening, I'm talking about the green chemistry, the advantage of green chemistry is, it allows us to do the same chemistry, with less pollution. That is the benefit of the green chemistry. And green chemistry is based on the 12 principles that are the green chemistry, based on green chemistry, as I said, 2 Nobel Prizes were given, and green chemistry allows us, to minimize the pollution, or otherwise, increase the atom efficiency, selectivity of the reactions, all that, we can achieve by catalysis. Catalysis is such an important field, everywhere in the industry and everywhere. Now, catalysis, how it works, as we know, basic principle is, to provide an alternate path whereby the less energy is needed for the reaction barrier to be crossed. That one is, that way you can less energy means you have reaction. Now, the catalysis, as we know, is a homogeneous catalysis and heterogeneous catalysis, and both have got their own benefits, Take example, if you compare the benefits and the problems associated with that, homogeneous catalysis, it is normally, the reactions are, very high rates, and then you get normally they do not easily get poisoned, and then high selectivity and mild reaction conditions, and reaction mechanisms are well understood. But the problems associated with that are, normally they are expensive, or otherwise, you can't recover the catalyst. That is the main problem. With the heterogeneous catalyst, the main advantage is, you can easily recover that because it is in a different phase, and then it can be reused again and again, and it has a long service life. But the problem, some of the problems are, these are normally having lower selectivity, and the mechanisms are not properly understood. And we focus on those 2 aspects, how we can improve the selectivity and how we can understand the mechanism aspect. Now, we use, number of materials in the heterogeneous catalyst, the different size of pore sizes, particularly in the fine chemical industry, the pore size is very important to achieve this high selectivity. Now we are going to talk about these materials as mostly the supports, so that we can achieve our reactions. Okay, sorry for that. It is somehow there is some problem coming. Okay, let us talk about the catalyst. When we talk about the catalyst, what is the best catalyst? First thing is, as we were talking, selectivity, high selectivity, and high efficiency of conversion, and the ability to work under mild conditions, and then so that you won't have the energy conservation, and then good solvents used, and recyclability of the material. Those are the aspects, if you basically look at the catalysis, how it works, normally if it is a heterogeneous catalyst, you have to see that, your reactant sits on the catalyst surface and the active surface, like what I mean, active sites, many a times, you have got some functional group like oxide or hydroxy group or otherwise amino group, something is there, which will allow the reactant selectively. And once the reaction occurs and readily it leaves, unless it leaves, it becomes a problem. That's why, we have to choose the active sites in such a way your reactants are selectively undergoing the reaction, Now take example, I talk about the mixed metal oxides and nanocomposites, and these mixed metal oxides are, more than one metal, or otherwise, there are more than one component is you have the composites, These metal oxides and these nanocomposites are, used, it's not a new idea. It has been there it is a multi-billion industry in petrochemical industry or otherwise in fine chemical synthesis and all that. And we look at what is the benefit of that is, if you look at the periodic table, in the periodic table, you see the strongly acidic elements and weakly acidic elements and amphoteric metal elements or metals, or then you have the weakly basic and basic. With those properties, different properties, like you have got, take example, you have a weak base, and if you have a strong acidic site, it will readily pick that one and allow the reaction, take example, And then when it comes to nanocatalyst, the advantage of the nanocatalyst is, you use small amount and spread it in such a way in the nanoparticle size, on the active surface. With that, you achieve a sort of a better performance from the small quantity of that. And normally, if you compare the normal metal oxides, which are also catalysts by themselves, then with the bimetallic or nanocomposites, the advantage of that is, this compared to the individual metal oxides, which lose their catalytic efficiency quickly, these nanocomposites, they last longer, and you can use it number of times, like 5, 6, 7, 8 times, depending on the nature of the reaction. Normally, mild condition reactions, the catalyst can be used if it is reaction is at high temperature. Most of the times they get deactivated. And you look at the green synthesis, what we are going to look at it, normally what we look at is, minimal waste and atom efficiency. That means almost all the molecules we use in the reactant are going into the product, and the high selectivity and the easily available materials. And we are looking at the one pot synthesis, like multi-components, more than 3 components going into pot and then undergoing the reaction. You need not to purify the intermediates or anything, straight away you put your reactants and get your final product. And all these are the benefits of the multi-component reactions. And you see a stepwise reaction, and you do the first reaction and take out the intermediate and react with another one in the next step, like that. The multi-component reaction, all the 3 or 4 reactants are put together and you get the final product. I want to show you a number of examples from our laboratories. Take example here, it is a 3-component system, and this is silver on zirconia. We did a lot of work on the zirconia supported. I will give you a few examples with zirconia before I go to look at the other ones. In this case, let us spend a little more time on this slide than the next ones, because very similar information you see again and again. Like it's a 3-component system. In this one, 12 novel indinopyridines have been synthesized using 2.5 silver on zirconia. How we decide that, a lot of groundwork will be there, as you normally in all the research, what it happens, you have to use the different loading of silver. First thing is, you have to scan various oxides, which can give you good activity. Afterwards, you combine the oxides, that's what it happens. Like in this case, silver and zirconia, they give good one, and you combination of that, we are looking at, like you see those figures there, 1%, 2.5%, and 5% loading of the silver. What it happens, 1% is too little and 5% is too much, and you get agglomeration or clambering of the research. What it happens, we have to use the different loading of silver. First thing is, you have to scan various oxides, which can give you good activity. Afterwards, you combine the oxides, that's what it happens. Like in this case, silver and zirconia, they give good one, and you combination of that, we are looking at, like you see those figures there, 2.5% and 5% loading of the silver. What it happens, the record is playing,
It's Surabhi Lilare. It's Surabhi Lilare. You please switch off your mic.
Can I continue?
Yes, sir. Sure.
Okay. Sorry for that. And if you see it, the 2.5% is a very nicely distributed. You can see the mapping, the color mapping. You can see how nice the silver is distributed as a particulate size, Now, as you see that one, the particles are very small nanoparticles, like normally about 10 nanometer size, With this one, what you achieve is, like 90 to 96% yield in short reaction time of 30 minutes at room temperature. You look at the conventional reactions reported, that one, like sodium hydroxide as catalyst, you take 6 to 8 hours, only 45% yield. That means, more than 50% of your material is to be not used. And again, recovering and separation, all that becomes a problem. Here in this one, you get almost everything reacted, 90 to 96% yield and at room temperature. I will show you a number of examples similar to that. Let us look at this one. Now, in this case, ruthenia and zirconia, in since functionalized pyridines, and at room temperature, the reaction, it is again in this also 2.5% ruthenia and zirconia. We have got the yields are very similar, 90 to 96%, and then reaction occurs in less than 20 minutes. The conventional reaction, with the triethylamine, it is like it takes 8 hours only with 64% yield. Here in 20 minutes, you get less than 20 minutes, you get 90 to 96% yield. And like that, here you see another is bismuth and zirconia. Bismuth and zirconia, you have got 1, 2, 3, 4 component reaction in ethanol and room temperature. And the products, again, you get in 91 to 98% yield. And all are 11 new. I'm not talking about their activity, etc. Some of these molecules have been, their biological activity also has been tested, And now it in 20 minutes and at room temperature, you get all the products in excellent yields, and it is reusable multiple times, like 7, 8 times without loss of activity. And conventional reaction, sodium hydroxide under reflex condition gives only 35% yield after 3 hours of the reaction. But here at room temperature, you get in 20 minutes and almost 91 to 98%. Here is the same catalyst used, but under different conditions here. In this case, it is a water as the solvent. Earlier, you saw the ethanol as solvent. Here, water as solvent. This reaction is, for the pyrazole derivatives. Here, you have the same 2.5%, but you get that, in 45 minutes at 80 degrees, the temperature reaction occurs, but excellent yields, you get 90 to 96% yields. That means sometimes, you can use the same catalyst in another reaction. As you can see the reaction, it's quite a good performance. And it involves the reactions, the 3 component reactions involves as you see, the mechanistic aspects, And now here is another simple reaction with a 4 component reaction using nickel on zirconia. Nickel on zirconia, here again, 2.5% nickel is loaded on zirconia. And then, the particulate size, like 8.5 nanometers. You can see the TEM image there, small particles of zirconia loaded, spread over on this zirconia support. And the reaction yields are quite good at room temperature, and ethanol as solvent, and less than 45 minutes, you can get the product. And 18 novel compounds have been generated, and you have the catalyst is recoverable. Almost all the catalysts are recoverable. Sometimes, you can get almost up to 8 to 10 times. And here, another example, here in this case, a 3-component reaction that of gadolinium on the zirconia, and it's quite an efficient one. In this case also, actually, it was 2.5% loading of that, and you got the reaction, very similar results, 90 to 96%, and then in less than 30 minutes at room temperature, 5 times it is recyclable. Here, another example on zirconia, that is the vanadium. Vanadium is a very good acid catalyst. That is now with that one, you get novel dihydropyridine derivatives. And it's again a four-component reaction, giving the products in excellent yields in less than 20 minutes. And as you see, most of the cases, 2.5 looks more optimum loading, but we have the cases where we have the 5% was doing better than 2.5 in some other cases. But like here, you get the yields are quite good in less than 20 minutes and at room temperature. This is with the yttria, and you see, look the similar, but the thing, exactly the same catalyst won't work another reaction. As you see, it has, we have to try and see, which performs better, and you modify the catalyst accordingly. In this case also, less than 20 minutes, you have the 1,4-dihydro pyrimidines and similar one, and these are different molecules, but there is a four-component reaction quite efficiently at room temperature. In 20 minutes we achieve the products in excellent yields. I want to show you some other materials like here, in this case it is only zirconia itself only functionalized. It is a pyridine diamine functionalized zirconia without any other loading. It's quite good, in this particular case, in the ethanol water system at 70 degrees in 3 hours, the yields were 80 to 91, and these were quite, you see, not that as good as the earlier case, but this is a different material without any additional thing. Now, I will show you here some other catalyst material like calcium hydroxyapatite is a very cheap material which is there in our bones, etc. Calcium hydroxyapatite, and you can load that with different, very nice material. You can modify that, loading with different metals, the trivalent or divalent metals, and you can achieve very excellent results. And in this case, ruthenium loaded. In this particular case, you see that 2 series of reactions have been done, and both in the water and ethanol system, 4-component reactions. You can see that in one series, both the series, you have the yields are quite good, and the 22 put together, 22 pyranopyrazoles have been synthesized, and in both the series, we had excellent results, 88 to 97% and reactions less than 30 minutes. To compare that, normally the other reflex conditions using stannous oxide as a catalyst, it takes 1 to 2 days, and with 80% yield, if you compare that with what we can achieve now in less than 50 minutes, less than 30 minutes, you can achieve 87 to 97% yield with at room temperature and with using a green solvent like ethanol and water. Now here we have another, like, magnesium oxide and hydroxyapatite, magnesium oxide. This one is again used in a 3-component reaction to get dihydropyrazolopyrimidines. And these ones, also you can see the yields are quite good, 90 to 97% at room temperature in less than 25 minutes. This catalyst is quite recyclable. And I'll show you some other materials here. In this case, nanocellulose on the hydroxyapatite. This one is quite a good catalyst in this one case, but it is not a multi-component reaction, because why I put this in, although it is multi-component, because it's an interesting reaction. Efficiency is quite good. You get the condensation. This particular reaction, you get 90 to 96% yield at room temperature in 15 minutes. The catalyst is recyclable up to 7 times. This nanocellulose is, you can also load other materials on the nanocellulose. In this case, we loaded that on hydroxyapatite. And this is another natural polymer, chitosan, that again on the hydroxyapatite. And this particular one was used for a 3-component synthesis in ethanol. And at room temperature, it gives the products in 30 minutes, quite good, quite good, and 86 to 96% yield. And all these materials, and although I'm not focusing on the material, all the materials are nanomaterials loaded on the support. Here, the fluoroapatite. Fluoroapatites are, although hydroxyapatites, when you have some fluorine, fluoroapatites are quite good catalysts and also support materials. In this case, bismuth loaded on fluoroapatite, this particular one was quite efficient, 90 to 96% yield of the 13 pyrimidine derivatives, and excellent yields in less than 35 minutes. If you see the atom efficiency in this particular case, almost all the carbon, 100% carbon capture and 98% atom economy. That means, almost nothing is wasted. Everything is going into your product. Now, this is another case of nickel loaded on the fluoroapatite. Fluoroapatite, you can see the very nice distribution of the nickel on the support. And in this case also, you have a four-component reaction ethanol. And this particular case, the reaction occurred at 50 degrees and the yields are quite good, 90 to 96%, and less than 40 minutes, you can get the products, and this material recyclable up to 6 times. And here we have another example that of the vanadium loaded on fluoroapatite. Earlier we saw vanadium on zirconia. Here is vanadium on the fluoroapatite. This again, we have 3 series of reactions, and 1, 2, 3, depending on the 3 series, you get all the products. And what is interesting, irrespective of what you have the substituents on that, you get the product yields are quite good, 90 to 97% yield in all the cases. Overall, you see 90 to 97% is quite good at room temperature, and recyclability is 5 times. The products you get straight away, take them and wash it, and you got them in the pure form. And I show you some other materials we used, like in this case, we used the samarium loaded on fluoroapatite that was loaded on the multi-walled carbon nanotubes. And with that, the thing is, what is interesting, all these, by themselves also have the catalytic activity, like multi-walled carbon nanotubes or the samaria, or otherwise, fluoroapatite, all have some activity. When you combine that, you see in this particular case, samarium loaded and fluoroapatite, and then on the carbon nanotubes, this one gives you 80 to 96% yields, and then, in less than 10 minutes at room temperature. Material is recyclable, and you can see, and in this particular case, it's not a multi-component reaction. I chose this one to show the sort of the material. Next one, I show you the multi-component reaction here, a 3-component reaction. Now, in this case, we have the titanium on the fluoroapatite, which is loaded on the carbon nanotubes. And this particular one, it gives quite efficient and 91 to 95% yield, and reaction occurs at room temperature in ethanol green solvent in less than 20 minutes, and material is very recyclable. And now I show you some other type of materials, hydrotalcite. Hydrotalcite is a very cheap material. Hydrotalcites, normally we can load different material. Hydrotalcite is our talcum powder, the face powder, what we use the hydrotalcite. This hydrotalcite, by loading here with the magnesium and vanadium carbonate on to that one, that gave us very good results at room temperature. Less than in 1 hour, we got 89 to 94% yields. And now you see the solvent is just water and quite good. And the same reaction, conventional reaction is, it takes 8 hours, only 54% yield. Here, now with sodium hydroxide, that you use there with sodium hydroxide. But whereas here we can get very, although it takes almost 1 hour, but the yields are quite good. Here is another one, zinc vanadium when you carbonate on the hydrotal side, this again we have 1, 2, 3, 4 component reactions, quite good, giving at not room temperature in water, giving the yield 92 to 98%. But in this case, it takes temperature 80 degrees. But the same reaction at 80 degrees, it takes 6 hours to give you 30% yield in the conventional methods. That shows, how efficient the reaction can become. Now,
sir, will it be possible for you to finish in
magnesium oxide, and it's a similar, here are 2 series of reactions we did in ethanol, and about 70 degrees the reactions, and 85 to 95 in one series, and 80 to 86 in other series, but less than 45 minutes. And then, it is quite recyclable material, and conventional reaction after 7 hours, it takes 30% yield. Compared to that, you get now the 90% yield quite efficiently. And
sir, will it be possible for you to finish off in 5 minutes?
Oxide, we used number of catalysts, organofunctionalized graphene oxide, otherwise, nanoparticles, nano zero valent particles loaded like that. In this particular case, organofunctionalized one, this particular 4 component reaction, it gives you the products in 93% yield in 2 hours at the room temperature, and catalyst is recyclable up to 3 cycles. Now I'll show you another graphene oxide. Here it is the manganese oxide loaded on reduced graphene oxide is quite good one. The reason is, although it is a simple conversion, it is straight away from benzene, you can get aniline with 100% selectivity. That is the advantage of this method. Normally you can't get benzene is cheapest, but normally you have to get the nitrobenzene, and from nitrobenzene you have to get the aniline, But here you can get straight away benzene converted to aniline with 100% selectivity and 77% conversion. And
sir, will it be possible for you to finish in 5 minutes more?
I will be finishing. I'm coming to the end.
Yeah.
Now, in this particular case, we have the complex coordination complexes. Coordination complex 3D supramolecular structure. And I will show you the metal organic frameworks in the next example. And in this one, a 4-component reaction using this cobalt and both cadmium metal organic coordination complexes to synthesize the pyranopyrazoles in excellent yields, 92 to 98% yield at room temperature and in less than 20 minutes. Another example is the metal organic frameworks. You can see that, here again, the metal organic frameworks are quite an excellent catalyst, they are a very excellent catalyst and very high efficiency. This particular case, at room temperature in 90 to 96% yield in 10 to 20 minutes, 15 to 20 minutes, get the 4 molecules combining to give you the final product very efficient way. And this is another organometallic framework for the 4 H-pyrons to synthesize the 3-component reaction, and very excellent efficiency, 91 to 96%, very much recyclable at room temperature reaction. In 40 minutes, you get the products, very good. And this is another organic frameworks, and this is also a 3-component, is a very recent one. Now you have the sulfur containing molecules here, and these ones, benzothiazolopyrimidines, and quite efficient reaction, less than 15-25 minutes at room temperature, excellent yields. And I want to, I'm coming to the end. Here I show you the eggshell. Eggshell also can be used as the powder, and almost from the egg, what we throw away, that powder, eggshell powder, actually that contains, as you can see that, what it has got the high calcium and carbonates, and with that, that calcium oxide and the carbonates, they are capable of doing the reaction. You can see that, a 4-component reaction with 98% yield and in 28 to 45 minutes. Excellent, 100% carbon efficiency and 98% atom economy. Almost all the molecules are going into the final product. And this is with the eggshell. Next one I will show you with the brick powder. Normally bricks, you can take the brick powder, and almost all the brick powders will have similar composition, minor variations, like it has got silica, iron, aluminum, calcium, magnesium, etc. And those oxides act as the catalyst. And now you have see that a 4-component reaction achieved 15 series of 15 different derivatives have been synthesized, 91 to 96% yield. And you can see that one, that is quite efficient, and recyclability is possible, but without recyclability, you can generously use your catalyst in this case. With that much, I tried to show you some of the examples, where you have the green synthesis. That means, using the catalysts and to achieve the excellent selectivity and the yields at moderate conditions, and using green solvents and using recyclable materials. With this one, you use very minimal solvents. With that, no harmful residues or byproducts are there, and highly selective reactions. And finally, I want to thank Professor Ajay Singh. He has a lot of energy. He sees that these things to happen. And the conference organizers for the invitation, and then my university who support me, and all this work is our students, my postdocs, and some of the people here you see, and there are some of my PhD and master's students and postdocs also. Finally, this is the message for the younger people, and thank you for everybody for the attention. A man can succeed at almost everything, anything, for which he has got unlimited enthusiasm. That is what is important. You want to get the zeal to achieve that, you can achieve that. And with that, this is Durban. That is, Durban beaches are, they are blue flag beaches. That means, you can take bath without any side effects. Even in the Corona time, you can do that. And thank you. That is our soccer stadium. Sorry for that, it took a little longer because of the confusion,
Yeah. Thank you, Professor Janalgada. An excellent talk for last 40 minutes. He started with the extremely popular sort of thing, like the introduction to nanodes, then the 12 principles of green chemistry, application of these green chemistry principles in the catalyst applications, and followed by the multi-component reactions in a single pot, mainly based on the zirconia materials, followed by the bismuth oxide, and up to the titania, and various, up to even magnesium oxide. So an excellent talk, giving a glimpse of whatever work he has done. I was going through all the references which he has quoted. A lot of work over the last 4 or 5 years he has cited in all those slides. Now the session is open for discussion. 2-3 quick questions can be answered. If anybody has question, he can ask directly. Because I personally have 2-3 questions. So, yeah. Yes. Thank you, sir. Actually, what we see is normally when we talk about anything nano or the surface chemistry part, sort of thing, we talk about the oxides only. Now, is it only the inertness of the oxide or any other properties which make them useful in catalyst applications? Just like 2-3 you talked about 2-3 times only about the carbonates, but mostly oxides. Why oxides only?
You see, normally oxides, they depend on the nature of the reactions. You see, the oxides, they allow once the the active site, when the reactant, most of the times your alcohol or something, that comes, when it sits on that, once the reaction occurs, immediately that leaves and the vacant site is readily available again. That's one of the reasons, normally some of the things, most of all the active catalysts, their active sites have to be recyclable. That means, that once the reaction occurs, it has to be available for the next round. And that is the normal oxides, they withstand high temperatures also, they are more thermally stable.
Right. And one more thing, sir. How do you recover the catalyst after getting your product?
Okay. Recovery of the catalyst, many a times, you can filter it off, otherwise sometimes, I didn't talk about that separation aspect. I didn't talk, sometimes you have got a iron or something there in that one, you can use the magnetic material, and normally some other cases, there are various ways, normally most of our cases, because our solvents are water and the ethanol, we do that by filtration, When you do that, you may lose marginally, not 100% you may recover, get 96 or 98% recovery. Normally when you recycle, whatever the shortfall you have to make up, But it's not
but
difficult,
for that
very
the product,
easy to.
yeah. But for that the product has to be insoluble in water.
Yeah, products normally they can be separated by that, that's not the problem.
Can I make a few points?
Yeah.
Yes, sir. Sure. Yes, sir.
Okay.
Anil Singh, sir, please.
Yeah, right. Thank you very much for allowing me. First of all, I think it's a very good talk at a very rather sad time, because yesterday we lost the father of catalyst, Nobel laureate Robert Grass. So I pay my humble tribute to him. As far as the lecture is concerned, it's a very good lecture, particularly the multi-component synthesis of some of the compounds, that too using very simple metallic systems. For example, benzene to aniline is a fantastic reaction that you have shown, and that too in a very simple catalytic way. However, these days I think the metals are avoided as far as possible in the industrial setup because of their poisonous nature and other factors. So I think to some extent, if you use the metals, then the greenness of that process is reduced. Particularly when you are trying to develop catalysts based on exotic metals like silver, gold, zirconium, and platinum, palladium, etc., etc. However, the catalysts based on, let's say, magnesium, zinc, iron, etc., they are fantastic. They are very, very good. Other point is, when you use natural systems like eggshell and bricks, then the reproducibility of the process would be perhaps, one has to really be very, very careful in that sense. Otherwise, I think my message would be that, as I said in my opening remarks earlier, catalysts have become very important today with regard to particularly making the platform chemicals. And it is very unfortunate that we don't have many economically viable catalysts and environmentally viable catalysts for industrial purpose today. We have many, but they are not really good at present time. And in Indian context, let me make it very clear, there is a real dearth of these systems. We are not working on this. That is why I said catalysts are very, very important. But as I said earlier, they must be economically and environmentally viable. If any process that doesn't conform to these two things, I think then we should try to look into other way. So thank you very much, Professor, for giving an excellent lecture and enriching us with very nice reactions, particularly benzene to aniline was fantastic. Thank you very much.
Welcome. Thank you.
Thank you, Dr. Anil Singh, sir. Is there any more question? Okay, if not, then let us thank Dr. S.B. Jonalgadda on behalf of the organizing committee of the conference. Sir, thank you very much for the excellent talk and sparing time with us. Thank you, sir. Now we move ahead to the second speaker, the second keynote speaker, Dr. Muhammad Abu bin Hassan Susan. Dr. Susan is a professor in chemistry of Dhaka University, Bangladesh. He received his PhD degree from Yokohama National University, Japan in 2000 and was awarded with VBL, JSPS, CREST, and Bridge postdoctoral fellowships. His research interest is in the field of material chemistry, in particular on nanochemistry, supramolecular electrochemistry, micellar catalysis, ionic liquids, anhydrous proton conductors, water structure, and polymer composite materials. He has 170 articles, including 17 book chapters and 18 proceedings, with 277 abstracts published as contribution in scientific meetings. He is a reviewer of more than 52 national and international journals. His research projects have been supported by many national and international organizations, including Ministry of Science and Technology, Ministry of Education, University Grants Commission of Bangladesh, Bose Center, Semiconductor Technology Research Center, Renewable Energy Center, World Bank, etc. He collaborates with 14 renowned laboratories and visited 11 countries of the world. He has nominated for award of FACS in 2005 and ISESCO in 2010. He received Dean's Award of Faculty of Science, Dhaka University in 2011. University Grants Commission Award of Bangladesh in Physical Sciences in 2011. In Chemical, Biological and Environmental Sciences in 2013. And United Group Paper Award in 2016 and 2017 for 7 articles. He received silver medal in the Society of Promotion of Education and Science, India in 2019. He is a member of many professional organizations and served as Joint Secretary of Bangladesh Chemical Society from 2011 to 14 and National Representative of Division 1 of IUPAC. He is a Fellow of Bangladesh Academy of Sciences from 2016. He has also been a Fellow of IUPAC. I welcome Professor Susan for his keynote address. The time given for this presentation is 30 minutes with 5 minutes of discussion. Professor Susan, sir, please.
Thank you. I think you can hear me, right?
Yes, sir. Yes, sir. You are clearly audible and slide is also visible.
Okay, thank you. So I am actually very honored. I feel very honored to have the invitation again. Now this time to international webinar on recent trends on science and technology. So as many of you know that there are many friends in Chhattisgarh there, including Professor A.K. Singh, and I am very happy to join you with you all again. And today, my address, as you can see, is focused on metal polymer nanocomposites with tunable morphology from water in oil microemulsions. Actually, some of you may be familiar with the use of water in oil microemulsions in my presentation. This is an important part of my research work, and I have used water in oil microemulsions as nanoreactor for many different purposes, including for the preparation of metal nanoparticles, core shell nanoparticles, semiconducting nanoparticles. So here actually I have extended the concept of the nanoreactor based on water in oil microemulsion for the preparation of metal polymer nanocomposites. So the basic principle is the same, but here I can share with you some results where we have shown that polymer nanocomposites can be prepared, including metal, with tunable size and morphology from such water in oil microemulsions. So I will try to finish within the stipulated 30 minutes time, but if it appears to be delayed, you can warn me before 5 minutes. So here is an outline of the talk. So we are going to use microemulsions as nanoreactors, as I already mentioned. So the purpose, as till now I have described, is for the preparation of nanoparticles, especially for the stock on metal nanoparticles. So after showing this, I will introduce very briefly on polymer nanocomposite. And as I have said that we are interested in this work on metal polymer nanocomposites. So we shall discuss on silver polyaniline nanocomposite. And here you can see the silver polyaniline. But here the polymerization itself will be started from the monomer aniline, and the polymerization will take place inside the core of the microemulsion. But for polyvinyl alcohol, silver polyvinyl alcohol system, the nanocomposite has been prepared starting from the polymer itself as the precursor. So although we have used the same microemulsion system, the approach will have slight difference. And then we shall conclude. So let me start with a brief introduction on microemulsions and the protocol for synthesis of metal nanoparticles by using these as nanoreactors. So microemulsions, we are familiar with this emulsion like milk. Milk is an emulsion, but microemulsion is similar, but the basic difference is that it is transparent, like clear and transparent, like a solution. This is thermodynamically stable, and this is optically isotropic. Preparation, usually it has two different phases, water, oil, and surfactant is used for the emulsion. And often we have to use the co-surfactant, especially for cationic or anionic surfactants. So these are, say, macroscopically, this looks like a solution, as I mentioned. These are homogeneous. These appear to be homogeneous. But if we check this under an optical microscope, we can see that these are not actually homogeneous. These are microscopically non-homogeneous because there are systems like myceli or inverted myceli. Myceli, reverse myceli in the system, and there may be water-rich and oil-rich domains separated by an amphiphilic fin. So this gives rise to some heterogeneity in the system. So microemulsion based on the composition, say, of water, oil, or the surfactant. There are many different types. These are called Windsor 1, Windsor 2, Windsor 3, or Windsor 4, something like this. The basic difference is, say, oil in water. That means water is taken in large amount and oil is only slight. Or it may be water in oil, so large amount of oil and water is only in a minute amount. And if these are comparable, this can give, say, Windsor 3 or Windsor 4 type microemulsion. We are in this work interested, or we have used Windsor 2 type microemulsion. So Windsor 2 type, as you can see in this figure, that these have these have in the system mainly reverse myceli. That means a hydrophilic core inside which can trap water. So this is of nano dimension. So any reaction that will take place inside the core, that will be in the nano dimension and in the nano confinement. That means it may be called a nano reactor. So actually that is the basic principle of our work. So we would like to clarify it further by showing the preparation of such reverse myceli dominated water in oil microemulsion. So we know that to prepare we need surfactant, co-surfactant, and two different phases, oil and water. And if these are in such situation, water is only small amount, then hydrophilic core is formed, as I have already mentioned. So the core is inside, and if there is a co-surfactant, so we can see that that co-surfactants are situated in the vicinity of the surfactant to make it a stable microemulsion. And these are reverse myceli inside the transparent phase. These are dominated mostly reverse mycelia are there. And since these are of nano dimension, this can serve as nanoreactors. So up to this, I think you have already been familiar with in my previous talks in maybe 2 years or 3 years back. And after that, actually exploiting this concept of reverse microemulsions, we have first of all tried to control the reaction environment. That means whether we can control the size controlling parameters of microemulsion. That means whether this core can be made smaller or larger by changing several parameters. And we have identified that yes, we have the choice, we have the option to tune the nano dimension by changing the water to surfactant molar ratio, by changing the type of the co-surfactant. This may be based on the chain length, based on the branching of chain in alcohol, or it may even be type of the surfactant. That means we can change the nature of the surfactant. It can be a cationic surfactant, an ionic surfactant, or even non-ionic surfactant. And the important thing, as I have shown, is that we want to control the hydrodynamic diameter of the water core. That means if it is smaller, it is quite understandable that any reaction that will say make some metals, so that will nucleation will start, and the crystal growth will be limited to a certain size because it is in a confined environment. So if it becomes larger, we will have the option of wider size distribution as well as larger sized particles. So we have to try to control the size of the core where the reaction will take place. And this can be done by changing these parameters, as I have already mentioned. And to check this, actually, we have taken the help of dynamic light scattering measurement, which gives direct opportunity to measure the core of the dimension from the measured hydrodynamic diameter based on the principle of dynamic light scattering. So let me now show how have we prepared metal nanoparticles using some of these parameters or such microemulsions. So in fact, we have shown silver, incorporation of silver in say polymer nanocomposite. So I will show silver as well as some other metals here. So basic principle is the reduction of metal salt by sodium borohydride, so which will give metal nanoparticles. So sodium borohydride is the reducing agent, and we want to carry out these reduction reactions inside the core of the microemulsions, reverse microemulsions. That means reverse mycelium. So in doing so, what we can do, so we can take two different reagent bottles. For example, we can incorporate metal salt in such a microemulsion, and those, since these are hydrophilic in nature, this will be trapped inside the core of the reverse microemulsion. And then if we separately add sodium borohydride, so that will be incorporated in another reagent bottle. Now, say if we combine this together, then these reverse microemulsions, which are separated will come closer to each other. They will coalesce, and what will happen? The metal and the reducing agent will have the opportunity to come closer to each other, and the metal salt will be reduced. In this way, you can see, and then a nucleation will start, and the crystal will grow up to a limit, because this is now in a confined environment. So by doing this, we can have metal nanoparticles. And to check, I shall show the key results here, that water content in the microemulsions, for example, water to surfactant molar ratio, as I have shown. So we have checked that by changing the dynamic light scattering, we can show that increasing water to surfactant ratio, say from 7.7 to 20.8, you can see that average diameter, this increases. Increasing by increasing water to surfactant ratio. That means we have a control, and same image of copper nanoparticles. You can see from these we have estimated the size of copper or iron or silver nanoparticles. And if we summarize these results graphically, we can see that water to surfactant ratio, if it is increased here, you can see average particle size is increased, because this is due to the increase in the hydrodynamic diameter. That means crystal growth, or the growth of the nanoparticles now becomes, have the opportunity to become bigger, larger, and therefore it is tunable. And we could establish in the similar manner that by changing other parameters, say co-surfactant or type of the surfactant, we can tune the size of the nanoparticles prepared by tuning the size of the reverse mycelium in the microemulsion systems. Okay, so now let us enter to our main task, introduction to polymer nanocomposite. Polymer nanocomposite, as we know, these are multi-phase material and one or more dispersed phases with 1, 2, or 3 dimensions of less than 100 nanometers. Since it is polymer, it is a wide range. So at least one dimension should be, at least one, but it can be more, no issue. But at least one should be of nano dimension. And it can be, say, organic polymer that can serve as the matrix. These are easily processable, biocompatible, biodegradable, good host matrix we know. And inorganic nanoparticles like metal nanoparticles, these often give our desired properties. It may be optical, catalytic, electronic, thermal, or electrochemical properties. And if we can make a judicious combination of these two, and if we can incorporate nanoparticles efficiently in the polymer matrix, we can have polymer nanocomposite. The target is to establish some synergistic effect between these two components. This may be enhancement of mechanical, chemical, or thermal stability, and it often, say this is metal nanoparticle, it will show the tendency to be easily oxidized or to undergo agglomeration. So polymer nanocomposites may help to avoid such agglomeration. Okay, so let us now move to specific examples, say 2 cases as I have the plan to show here. One is silver polyaniline nanocomposite and another silver polyvinyl. So let me start with silver polyaniline nanocomposite. Polyaniline, we all know that this serves as a conducting polymer, and silver nanoparticle that can be a dispersed phase in this conducting polymer matrix. And the silver nanoparticles has properties that are suitable for biomedical applications. So we may try to use polyaniline-based nanocomposites for biomedical application by exploiting their antibacterial or antimicrobial activity. So we know about polyaniline. This has a very facile synthesis route. Monomer cost is very low. This is the environmental stability and so on. And this also has good antibacterial property. And silver, this is from ancient times. It is known that it has broad spectrum biocidal activity, extraordinary bacterial inhibitory property, and it can be used at very low concentration, and which shows negligible toxicity toward mammalian cells. And if we can combine these two to have a polymer metal nanocomposite, so we can have highly efficient multifunctional material having enhanced antibacterial activity for from synergism among these two components. So we also know that polyaniline, this is taken from literature or textbook, that polyaniline exists in different forms. So say here are the forms. So, but not all the forms show the necessary antibacterial activity. If I would like to check this emeraldine salt, in fact, or the emeraldine base. Say, if you compare these two, you can see that in the base form, no effect on the gram-negative bacterial growth and weak antibacterial effect against gram-positive bacteria, while the salt form has stronger effect on gram-negative bacteria and antibacterial effect against gram-negative and gram-positive bacteria. So we prefer to get the salt form so that we can have a better antibacterial activity. So how to prepare such polymer nanocomposite? So preparation is simple. I have said that we can take a microemulsion. Here we have taken a non-ionic Triton X100 based microemulsion. And these microemulsions, if we add any aniline and hydrochloric acid, silver nanoparticles in the Triton X100 microemulsion. So here you can see that we can use ammonium persulfate and we can sonicate, and by these in the microemulsion, the polymerization take place. And in the first step, silver nitrate is reduced to silver, and we can have the polymerized polyaniline. These two can give us the silver polyaniline nanocomposite. So to characterize, we have actually used dynamic light scattering measurement. You can see that polyaniline, if you prepare from bulk, it has 190 nanometer or something like that. And if we prepare from Triton X100 microemulsion, the size becomes reduced. And even after the incorporation of silver in polyaniline in Triton X100 TX100 microemulsion, the overall hydrodynamic size, remember this is hydrodynamic size, and the true size is definitely smaller than this because these are hydrated form. So this is 141 nanometer. And from same images, we can see that polyaniline, say this is from microemulsion, only polyaniline, and silver polyaniline from microemulsion. So, and also I have for comparison, we have shown the bulk synthesis. So polyaniline and silver polyaniline composite nanogranules of smaller dimensions are obtained from TX100 microemulsion. Even polyaniline can be formed as nanogranules if we prepare from microemulsions. And we have checked the surface charge of such materials, the composite, and as well as the silver nanoparticles, and we have seen by electrophoretic light scattering measurement that the zeta potential have the necessary negative values here, and these show that these nanoparticles are, when confined in say microemulsions, are quite stable. So here I would like to show the mechanism of formation of silver polyaniline nanocomposites using water in oil microemulsion. So as a whole, as I have shown earlier, so metal salt, so this is reduced to metal in the microemulsion when sodium borohydrate is added to it, and then say here we have added polyaniline, and these undergo polymerization reaction using ammonium persulfate, and while polymerizing, they have the silver incorporated inside, and we get in situ silver polyaniline nanocomposite inside the polymeric matrix. So silver nanoparticles here coordinate polyaniline chains and aggregate through various interchain and interchain interactions. Okay, so the last part is here, say silver polyvinyl alcohol and silver polyvinyl alcohol nanocomposite film. So for this, the main difference, as I have shown, this is non-conducting, and it is very difficult to carry out, say, polymerization inside the microemulsion. So we have taken a commercial polyvinyl alcohol polymer and used as metric phase. Just solubilized this, it has good solubility. So it was solubilized in microemulsion, and we used silver nanoparticles like before and tried to prepare the non-conducting polymer nanocomposite from this system. So we have mentioned about the importance of silver here for polyaniline. This we know that this is non-toxic, biodegradable. This is a strong host material property for metals and the excellent thermostability. Very interestingly, it has very good water solubility. And if we can prepare a nanocomposite, especially in the form of a film, the film may fulfill several conditions for wound dressing. It can protect the wound from side infection, absorb the wound fluids and exudates, give elastic, non-elastic, toxic, biocompatible, and biodegradable dressing material. So our target is not only to prepare nanocomposite to ensure application, we have also tried to prepare this in the form of a film. So the preparation is similar. Here we have the starting precursor polyvinyl alcohol. We have prepared a solution and we stirred, subsequently we cooled, and then so we have transferred this to microemulsion, and then say we have polymer matrix incorporated in the microemulsion, and then we have added silver nitrate and the reducing agent here, and we got the polymer matrix formed inside the core, and then we centrifuged the material and converted by casting to plastic petri dish to get the silver polyvinyl alcohol film. The preparation is rather very simple. And we have characterized mainly by optical transmittance and reflectance spectra, as you can see. And you can see that no noticeable absorption in the visible region for polyvinyl alcohol film. And so we have a sharp increase in the range of 210 to 248 nanometer due to polyvinyl alcohol polymer band gap. And you can see there is a valley here at about 400 nanometer. And we know this is for silver polyvinyl alcohol film. And this is due to the incorporation of silver. So this show the evidence of the formation of silver polyvinyl alcohol composite. And FTIR spectra also shows that the band at 1322 per centimeter is due to the coupling of weight in plane vibrations with the CH wagging vibration. And a change in the intensity of the band at 1322 per centimeter compared with the band at 1420 centimeter, this is noted, and this is due to the decoupling between OH and CH vibration. That means this is also another indication of the formation of a polymer nanocomposite, and the bonding interaction may be shown like this as shown in the scheme. And same image we have actually compared by preparing the within the microemulsion as well as in situ synthesis without, say, the microemulsion. And in the first two figures, you can see that uniform distribution of silver nanoparticles on polyvinyl alcohol film is noted, and the surface becomes very smooth and film surface. But for in situ synthesis without microemulsion, you can see that there are bunches of silver nanoparticles on PBA film. There are some sort of agglomeration or not uniform distribution. And more importantly, you can see there are pits and cracks on PBA film surface. That means we cannot have a smooth surface. So this clearly shows the importance of the microemulsion systems for use as nano reactor for the preparation of the polymer nanocomposite. Okay, so we are actually at the end of the lecture. I would like to conclude. So there are basically two major conclusions. First, metal nanoparticles of tunable dimensions can be prepared by altering different parameters of water in oil microemulsion. This is the first thing. And second thing is that silver polyaniline nanocomposite and silver polyvinyl alcohol nanocomposite film, as we have shown, can be very successfully prepared using water in oil microimmersion method with narrow size distribution. So actually, this is a group picture, and I am sure that Professor Singh and some other colleagues from there might know some of us here. So we have established a material chemistry research lab in Dhaka University, and I have been fortunate to welcome some of you in our laboratory. And due to COVID-19 pandemic, as you know, we have been distracted from each other, but I do believe that a normal world will prevail very soon, and we can meet each other in Bangladesh or India. Thank you.
Thank you very much. Thank you very much, Professor Susan, for the excellent lecture, starting with just the glimpses of emulsions, the micelles and reverse micelles, then restricting the particle size of the nanomaterials by using the emulsion part, and followed by some applications in the composite preparation. Sir, I have one question. Have you tried with some biopolymers? Like we are working on, our research group is working on chitosan based materials for water treatment. Have you tried with some biopolymers like chitosan or cellulose also?
Okay, so that is a very nice question. Actually, we have been involved. So we have started with actually, you know, that hydroxyapatite. So first of all, we tried with eggshell and shrimp shell. So from those, we have successfully prepared nano hydroxyapatite. So that has been successful. And next, we have started with some cellulose nanomaterial, and it also we have not yet published. This results, some of these are published, but hydroxyapatite also we have published to some extent. And for cellulose results, we will publish it soon. But this works for cellulose as well. For chitosan, we have not yet used, but surely the principle should work for biomaterial like chitosan-based materials as well. There is actually no, because the basic thing is that whether you can confine your biomaterial inside a micellally dominated or reverse micellally dominated core. If it is hydrophilic, use reverse micellally dominated system, or if it is hydrophobic, use the micellally dominated system. So if you can make these changes, it will show promise to prepare all interesting biomaterials. Okay.
Okay. Thank you very much, sir. If any other question is there, question is welcome.
Can I ask something?
Yes, Professor O'Neill.
Yes,
Kumar
sure,
Singh.
sir.
If there are no one else, I mean, if the younger students are not there, then I can pitch in. So if you allow me, then I'll.
Yes, sir, sure. Sure, sir. Singh, sir.
Okay. So first of all, Dr. Hassan, thank you so much for very well structured presentation with very good slides. Very good. I just want to comment on the Mr. Chairman's point also. I think you must be aware of late Professor Janos Fendler, where he has done a lot of, he has used chitosan and other kinds of biomaterials and tried to make construct inverted micelles and make such kind of particles, etc. Long ago. Anyway, so that I think you can refer the book Biomimetic Chemistry by Janos Fendler from Syracuse University, and that will give you a lot of information on that. Next point is about the talk which Dr. Hassan presented. I think I noticed that you have used non-ionic Triton X100 neutral this thing surfactant. how about no surfactant like AOT, for example, or DAP carboxylate, which are also very, very common? If they have better results as far as the size control is concerned, I don't know what is your experience. But
Yes.
AOT is a very common surfactant for making the inverted micelles in many systems. Uh, I believe that the water pool size, that is omega 0 value, water surfactant molar ratio would also depend on the type of surfactant that we are using. So would be the water pool size control, whether the water pool size is of omega 2 or 4 or 8 or 10 or 24. That also will depend on the type of surfactant. So we are showing the surfactants. So whether all these surfactants, SDS of course is not a good example because that is normally used in normal micelles.
Yes.
But AOT, I think, and the carboxylate one, the mixed with the co surfactant, DAP and co surfactant as a carboxylate group. So these are also very important surfactant for such kind of studies. And the last point is, I think one of the basic issue that remains in this area of research, which has been going on for quite some time, and many researchers across the globe are using this, how to control the size of the water pool, number one, and how to control the size polydiversity of the nanoparticles that are formed. And I noted that your polydiversity was I think somewhere 200 to 400 nanometer, sorry, 100 to some 250 nanometer in one of the cases, perhaps copper and iron nanoparticle when you silver nanoparticle that you are making. So that basic issue has to be dealt with. I hope younger people will take it up. My own experience has been, let me share with you, we made a nanoparticle of organic molecule, very low molecular weight organic molecule called cholesterol. And the paper is published, you can check with my name. Control of size of nanoparticles in inverted micelles. And I think still perhaps that is maybe one or maybe 5 papers published so far. That is a very basic issue that one has to address if you want to really make success in this. Rather not success, but better success.
Yes, yes.
How to control this, the size diversity. So thank you once again very much for a very nice presentation. I'm very much enriched by your lecture. Thank you, sir.
Okay, thank you. So let me start some responses from the last. So yes, the main issue actually, as you have mentioned, to control the dimension of the water pool, because if it is larger, so there will be the chances of polydispersity. That is very common. So it should be as small as possible so that the growth process is really restricted. So for these, we have shown, I have shown only the summarized portion actually because of the time constraint. One idea is to control the water pool, you have to change the water to surfactant molar ratio. And if in doing so, I have shown that if we increase this, so you can see if you increase the water to surfactant molar ratio, the core dimension increases. This has been confirmed by dynamic light scattering measurement. So you can see that progressive change and size distribution also. And another parameter we have discussed is type of the co-surfactant. And this may be based on the chain length. If you if you increase the chain length, so here, so that means the chain length is increased. You see the inside, the co-surfactant. So that means the chain length will further stabilize and the mycelium size will be, the core will be smaller. Another option is, this is also confirmed by dynamic light scattering measurement by showing the results for butanol, pentanol, and hexanol. This is another way. And you can also change the branching of the chain in an alcohol. That means the co-surfactant. If you have branching, so there will be steric effect. And you can see that you will have the smaller core dimension. And finally, this has also been established by dynamic light scattering measurement. And the second point that I have shown only results of CTAB, SDS, TX100. Definitely, SDS is not a good choice. So these are some conventional surfactant. And we feel that, so for to apply, if we want to use these nanoparticles while in confinement in the microemulsions, we have to choose some non-toxic and good surfactant, compatible surfactant system. And AOT, we have started experiment, but we have alternatively started some other surfactant like Twin 20, Twin 60, Twin. You know that there are a wide variety of twin surfactant, and those also have shown successfully the control of the water pool, and those could also be used as nanoreactor. And AOT, this we have just started. We have not shown any surfactant, but we have also been suggested that, like you, in another conference, we were suggested that you can start with AOT. And we believe that AOT will also show the similar promise. And regarding the first, your first comment, yes. So first comment was, I think, as a whole on the process, right? And we have been trying to prepare such a polymer nanocomposite and other system. And as you said, for biomaterial, I shall check your paper also. I have not yet read, and I know I have often checked your profiles and publications using SciFinder, and I believe that I can find it out today to get new ideas. And we are also interested in biomaterials. So your comments will help us to extend our work further for biomaterials. Thank you.
Thank you very much. Yeah. So if there is no more question, and since we are running a bit of lack of time, so we can move ahead. Let us thank Professor Hassan Suzan from Bangladesh for an excellent talk. And let us thank Professor Singh also for making it a beautiful discussion forum so that the youngsters can get some ideas about it. Thank you very much. So now, on behalf of the organizing committee, I thank both the keynote speakers, and I hand over the mic to the organizers once again. Thank you very much.
Thank you, sir. I think after 20 minutes, we will proceed oral presentation of the student. So all participants are requested to attend the presentation after 20 minutes. So time is I think 1:45. So
okay, we can start at 1:45, sir.
1:45, that is okay.
Right.
So all participants are requested to join at 1:45 for oral presentation.
Okay, sir.
Thank you.
Okay, sir. Shall we end the meeting?
Yes, we will join at 1:45.
Okay, sir.
Okay, sir.
प्रियंकाला सांगून ठेवलंय मी.
Sir, shall we start?
I think participants have been joined already. So presentation will be started.
Yeah. Sir, should I go ahead?
Oh, yes, sir. Yes, sir.
Good afternoon, sir.
Okay. Namaskar, Vijay ji.
Yeah. Namaskar, sir. Good
Namaskar,
afternoon
sir.
to one and all present over here.
I think Professor Patra is not there.
Yes, sir, I'm here.
Okay, sir.
Yeah.
Yeah. Take. Okay, sir.
Okay.
Thank you, sir.
Thank you,
So a very good afternoon to one and all. We are starting the second session of this first day of oral presentations. We have two eminent judges for this particular session. We have Dr. Gautam Kumar Patra, who is a professor in Department of Chemistry, Dean School of Physical Sciences, Guru Ghasidas Vishwavidyalaya, which is a Central University, Bilaspur. And along with him, we are having Dr. Vijay M. Tangde, who is Assistant Professor at Postgraduate Teaching Department of Chemistry, Rashtrasanta Tukadoji Maharaj, Nagpur University. In this particular session, we are having 12 presentations by various young presenters. 2-3 things I would like to inform all the presenters that the time allotted is 8 minutes for presentation and 2 minutes for question answer session. There are 50 marks allotted to all the presentations, which include innovation in the research idea, application of PowerPoint tools, communication and presentation, time management, and answers to the question. So all of these have been given some weightage. So all of you are requested to stick to the time and finish within 8 minutes. There will not be warning bell as such thing, but you have to finish within 8 minutes. And after 8 minutes, there will be a rapid 2-3 questions from the jury members. So let us start with the first presentation by Surabhi Lilhare. Surabhi, your time starts now. Surabhi, unmute yourself.
Sir, slide is visible?
Yes, slide is visible. Your voice is also audible. Please go ahead.
Sir. Thank you, sir. Good afternoon, sir. My name is Surabhi Lilhare and my topic is removal of arsenic methionine functionalized magnetic nanoparticle in trapped calcium alginate beads. These are content. Introduction. Arsenic is highly toxic and carcinogenic in nature. Arsenic can be found in both organic and inorganic forms as trivalent arsenic and pentavalent arsenate.
Please move your slide. Just a minute. Yeah, your slide is not changing. We can see just first slide only. Kindly make it full screen.
It fully.
Or press F5. Press F5 button from your keyboard.
Sir,
Just stop presenting and again screen share. Yeah, this was okay.
Yes, now we can see it in the full screen.
Okay. Okay, go ahead, Surabhi.
Okay, sir. As trivalent arsenate and pentavalent arsenate, arsenic 3 is more toxic than arsenic 5. Inorganic arsenic compound are more harmful and toxic compared to organic arsenic compound. The maximum permissible limit for arsenic in drinking water is 10 microgram per liter as WHO. The maximum permissible limit for arsenic is drinking water in 10 microgram per liter. Several techniques were reported for removal of arsenic from water, such as precipitation, coagulation, ion exchange, and adsorption. Among these techniques, adsorption is cost-effective, easy to operate, and high efficiency. Synthetic pathway of MFM and ABS. The nanoparticles were obtained by co-precipitation. Ferric and ferrous ion were co-precipitated by ammonium 100% of methionine in double distilled water, then obtained MFPS. After adsorption, sodium alginate dissolved in double distilled water, then modified MFMNPS was added. The mixture was added dropwise to the calcium chloride solution and MFMN ABS were obtained. This slide shows that the removal of arsenic in the biggest concern of human beings, which can be easily to operate the removal through the MFMN ABS due to cheap and eco-friendly adsorbent for the removal of arsenic. Result and discussion. XRD pattern of MFMNPS and MFMNABS before and after adsorption shows characteristic peaks, which is indicate that the standard GCBDS data reported for iron oxide nanoparticles as well as methionine-coated iron oxide nanoparticles. The material shows sharp peaks, crystalline nature, small size, and these results matched with the plane of the cubic structure of iron oxide. FTIR analysis. The broad and sharp peaks indicates at 3,434 centimeter shifted to 3,432 centimeter and 3,458 centimeter inverse are ascribed to stretching vibration of OH and NH2 stretching. The weak bands at 2,921 and 2,855 centimeter inverse is due to CH stretching vibration. And the peak 1,628 centimeter assigned to asymmetric stretching of NH3 plus to shifted 1,631 centimeter inverse and 1,632 centimeter inverse. And the additional peaks at 1,414 centimeter inverse in MFMN ABS before adsorption is due to COO minus stretching of sodium alginate. The weak bands observed at 1,389 centimeter inverse is due to stretching vibration of C double bond O. And the peak at 1,037 centimeter inverse shifted to 1,028 centimeter inverse and 1,026 centimeter inverse is due to CO stretching vibration and the presence of a band at 556 centimeter inverse and 562 centimeter inverse and 560 centimeter inverse is due to vibration of Fe bond in ferric oxide and CSC stretching mode. TEM image. The size of particles are distributed in the range of 6 to 20 nanometer and majority of particle size are between 12 to 14 nanometer. Most particles are scattered, but some are aggregated, indicating stabilization. And SAED shows that diffraction rings with bright spots indicates the polycrystalline nature of the adsorbent. The same analysis, figure 5a indicates that the surface are much smoother as compared to the surface of MFMNBS. Figure 2 indicates that the after cross-linking with alginate, MFMNABS exhibit rough, wide cavities and irregular pores. And figure C shows that aggregate with narrow cavities. The effect of pH. The sample was adjusted using 0.1 normal HCl or NaOH. It was found that the percentage remol was maximum 7 to 7.5. Thus, pH 7 was used for further studies. And the point of zero charge for MFMNABS value was found to be 7.66. The surface is positively charged below this value, and a small amount of anionic species are adsorbed due to electrostatic attraction in the pH range 7 to 7.5. However, when the pH is higher than the 0.0 charge value, the adsorbent surface is negatively charged due to repulsion forces. Adsorption may also be due to strong chelation via sulfur and amine group of the adsorbent. Nitrogen and sulfur atoms are potent donor due to presence of lone pair of electron. Effect of adsorbent dose. The greater number of vacant site on the adsorbent, the greater the capacity of adsorption. The percentage remol indicates from approx 92% to 95%, but afterwards the remol remained constant. The optimum dose was 1.6 gram. Effect of contact time. The maximum percentage removal was found to be 94.9% at 110 minute, and the removal efficiency was highest at 1 site are available for adsorption of arsenic ion at low concentration, as well as less active sites are available for adsorption at arsenic at higher concentration. There is a very slight improvement upon an increase in the arsenic amount, more noticeable for the low concentration, showing high efficiency. Adsorption isotherm. The data shows that Langmuir isotherm model was the best fit with the R square equal to 0.989 compared to Freundlich and Temkin isotherm. In addition, the value of dimensional separation factor RL was found to be less than 1, which confirmed that the adsorption of arsenic in a favorable process. Adsorption kinetics. Adsorption of arsenic by MFMNABS was modeled using pseudo first order, pseudo second order Ilovich model and intraparticle diffusion model. To explain the kinetic data, the pseudo second order kinetic model shows the highest R square value 0.9998, indicate that the second pseudo order is followed by adsorption process. Thermodynamic parameters. The slope and the intercept of the linear plot of ln/kd n versus 1/t. Enthalpy has a positive charge, confirmed the endothermic reaction, and del S has a positive value, suggest randomness increases. The Gibbs free energy was negative value, that the adsorption of arsenic on the MFMNABS is favorable and spontaneous at all temperature. Reusability. Desorption studies were carried out by the use of NaOH solution as the desorbing agent, and the adsorption-desorption cycle were used 6 in number of the cycles. And the mechanism, the figure shows that the possible interaction of methionine functionalized groups is supposed to the throw nitrogen, sulfur, and oxygen donor atoms. As figure shows, the carboxylate ion of amino acid can interact with Fe3 plus by either bidentate or unidentate. Nitrogen atom of amine groups, a potent donor, can make coordinate covalent bond with Fe3 plus, and sulfur atom is also expected to be a potent donor atom due to its lone pair of
Your
electrons.
time is over.
There is a comparison. Many adsorbent with high adsorption capacity are reported for arsenic as well as total arsenic, and only few adsorbent with high adsorption capacity are repeated for arsenic due to as non-ionic species around 7 to 7.5. These are conclusion. The reported the procedure is a reported
Yes,
cheap, environmental
Your
friendly.
time is over, Surabhi.
Okay, sir. Thank
Surabhi,
you.
your time is over.
Acknowledgement.
Yeah. A few questions from the judges, please.
Thank you, Surabhi, for your nice presentation. Just I have few queries. So you told that arsenic 3 is more poisonous than arsenic 5. Why it is so?
Sir, arsenic 3 is more toxic than arsenic 5 due to higher solubility. And excretion of arsenic 5 is dependent on valence state, and from arsenite has a slower excretion rate compared to arsenate.
In your presentation, you didn't show us that the function of the calcium alginate bead. So what is its function? In the title you have written, na?
Yes, sir.
So you have not discussed it anywhere. Okay, I have finished.
Okay, sir.
Surabhi,
Yes, sir.
did you carry out beta analysis?
Yes, sir.
Okay, but I could not see your beta analysis in the presentation. Specifically, that's why I asked. What was the surface area? Is there any relation? Is there any relation of your adsorption capacity and surface area? Anyway, okay. Thank you, sir. Thank you, Surabhi.
Thank you
so much. Surabhi, I have one question for you. You told you have shown in your mechanism that there is attractive forces between arsenic 3 and the ligands which are there.
Yes,
right?
sir. Yes, sir.
Does arsenic exist as arsenic 3 plus ion, or it is in the form of an anion? Actually, arsenic exists as arsenite.
Yes, sir.
And it is negatively charged. So what type of interactions you are expecting, or you have shown, are they correct?
Yes, sir.
Because if it is negatively charged, will it interact with the lone pairs of electrons on nitrogen and sulfur and oxygen?
Yes, sir.
Okay, so you think about this, right? Okay, thank you very much. We will move ahead with the second presentation by Dr. Shweta Kumbaj. Shweta, are you there?
No, sir, she is not here.
Okay. Next presentation is number 3, Swati Agrawal. Swati is there?
Yes, sir.
Yeah, you can share your screen and you can start your presentation.
Yes, sir.
And if possible, you switch on your camera also.
Yes, sir. Sir, there is something wrong. Sir, slide is visible.
No, we cannot see it.
Okay.
You just stop sharing and again screen share. Yeah, now it is visible now.
Okay. So am
Yes,
I audible?
please start. Yes, you are audible. Your screen is also visible. You can start immediately. Yes, Swati, go ahead.
Yes, sir. Good afternoon, sir. My name is Swati Agrawal for Department of Botany, Government VYT PG Autonomous College, Durg. And I'm doing this presentation under the supervision of Dr. Satish Kumar Singh, sir. It's not moving. Here is my content, introduction, methodology, result and discussion. Conclusion, acknowledgement, and references. So first of all, introduction. Nanotechnology is a new and emerging technology with the wealth of applications, and it involves the synthesis and applications of materials having the dimensions in the range of 1 to 100 nm. Nanoparticles is not a new thing. It is we found in volcanic eruptions, and it is a high surface area, high reactivity, particle morphology, tunable pore size, and it also known as a magic bullet, which can target the particular cellular organelles in plants to pass their content. And it increasing the applications in various areas such as medicines, textile, pharmaceutics, cosmetics, and environmental remediations. Here I'm using the green synthesis method for this nanoparticle synthesis. Basically green synthesis is a bottom-up approach. It is similar to the chemical reduction, where an expensive chemical reducing agent is replaced by extract of natural product. Natural product means like plants, plant parts, bacterial part, algae, something like this. Biological entities possess a huge potential for the production of nanoparticles. Green synthesis of nanoparticles using numerous kind of biological substances such as bacteria, mold, yeast, algae, and plant extract. In recent years, the auspicious anti-cancerous potential of nanoparticles, metallic form of gold, silver, copper, and many more metals are progressively being using for the synthesis of nanoparticle as a green synthesis method. And copper-derived nanoparticles is a challenging due to its cost effectiveness. Here the flow chart for metallic nanoparticle synthesis. We can use a plant parts and microorganism. Like plant, we can use leaves, stem, flower, fruits, roots, and microorganism like bacteria, algae, and fungi. So method is basically two methods. I have been using biological methods, which is also known as a green synthesis method, which is non-toxic. And metallic nanoparticles like gold, copper, iron, zinc, silica, platinum, selenium, and palladium can be synthesized by this method. And here the some uses: antimicrobial, antipathogen, mosquitocidal uses, cosmetics, medical appliances, drug delivery, cancer, and environmental issues. Sorry. So here's something about my plants, which I have chosen for this work. Tinospora cordifolia, which is also known common name is a gujro or giloy, gucci, moonseed. It is a herbaceous vine of the family Manispermaceae, which includes the 34 species, which several herbs were used as a traditional medicines by indigenous groups and throughout the tropical and subtropical parts of Africa, Asia, and Australia. It contains numerous of alkaloid, terpenes, lactones, glycosides, steroid, phenolics, aliphatic compounds, polysaccharides, and many more. In Ayurveda, Tinospora has been used over the centuries to treat various diseases like diabetes, high cholesterol, allergic, arthritis, hepatitis, fever, etc. Recently, Indian Ministry of Health and Family Welfare recommends the consumption of giloy for management of mild COVID-19. So my plant sample collection was the local region of Durg, Chhattisgarh. Durg is an urban city of Chhattisgarh. And my extract preparation is I using the standard methodology for followed this work. First, fresh part of the plants were washed tap water and then deionized water in order to remove the dust particles and other impurities, and kept for the shade drying, and then fine powder were used for extract preparation. And for the extraction, I used Soxhlet method, and aqueous extract of this plant were prepared. It was kept for the further analysis. These are the plant sample which are kept for the shade drying and the powder sample. These are the extraction of sample Soxhlet method. Now I have qualitative analysis of phytochemical, which is a preliminary phytochemical analysis where the phenol, flavonoid, saponin, steroid, glycosides, and terpenoid tests were performed. Next, the preparation of copper nanoparticles. Copper nanoparticles, 0.1 molar copper sulfate solution, which mixed with the plant extract, and we found a leaf extract with copper nanoparticles after some time, and leaf extract to change in the color in leaf extract to green indicate the formation of copper sulfate within the few hours. Result and discussion. Here's a phytochemical analysis. I tested a phenol, steroid, flavonoid, glycoside, saponin, and terpenoids, where terpenoids was absent in this leaf sample, and phenol test reagent is 2% FeCl3 solution, steroid for Lieberman test, flavonoid alkaline reagents, and glycoside kilocalani test, and saponin for shaking in test tube. This method was used in this work. Here's a characterization. So characterization, I use the FTIR analysis in this study. I have found the copper sulfate nanoparticle in this plant leaf extract. Peak was observed in 3,329 centimeter inverse for hydroxyl group, and 2,740 centimeter inverse, and 1,856 centimeter inverse for aromatic compounds for CH stretch, and 1,629 centimeter inverse for CC stretch, and 1,081 centimeter inverse for CO stretch. Here's a graph for the FTR analysis. Conclusion: based on the study of nanoparticles, and I use a green synthesis method for copper nanoparticle synthesis by using locally available plant as a reducing agent. This study covers their preliminary phytochemical studies and characterization by FTIR, and this will surely help in plant-based drugs. Basically, copper is a very cost-effective, so that's why I chosen this metal. And green synthesis are very less toxic, so that's why I've chosen the green synthesis method. And Tinospora plant, Giloe, basically known as a Giloe, which is a very highly recommended for the health purpose. Acknowledgement. And here's the references. Thank you, sir.
Okay, thank you. A few questions from the judges, please.
Yes.
Thank you, Swati.
Thank you, sir.
Achha. Do you know some another method for the synthesis of copper nanoparticle using this type of green synthesis?
Sorry, sir.
Do you know some other method by which copper nanoparticle can be synthesized by using?
Yes, there is a chemical method also.
I am asking for that your green method, like your method.
Green synthesis method, no, sir. Soxhlet extraction, for extraction, I am using the Soxhlet method.
I have seen that you have characterized the nanoparticles only by IR. Do you know some other method?
For characterization?
Yes.
Yes, the characterization for UV visible spectroscopy and SEM, TEM also there. But sir, my work is on progress. That's why I just done with FTIR.
Okay, sir. Next, please.
Swati,
Yes,
how did you confirm that nanoparticles are synthesized?
Sir, I have taken this plant Tinospora, which has extract was a very dark green in color. When it mixed with that copper sulfate solution, the color changes indicates the copper nanoparticles are formed, and characterization also confirm the synthesis of nanoparticles.
But then you did not characterize it using same or time. You
Yes,
characterized
sir.
it using FTIR. So how did you confirm that whether it is a nanoparticle?
So is one of the method for characterization, maybe.
Only FTIR cannot tell you, na?
Yes, sir.
Okay. Is it a MSc dissertation work or PhD work?
It's a PhD work, sir.
Okay. Okay. Thank you, Chairman. Sir,
Okay.
thank you.
Yeah. So thank you very much, Swati.
Thank you.
We'll move ahead to the next presentation by Dr. Sarabjot Kaur. Dr. Sarabjot Kaur, are you there? No. If Dr. Sarabjot Kaur is not there, we can move ahead to the next. Sachin Shende. Sachin Shende, are you there? Sachin Shende. Okay, next is Prachi Verma.
Yes,
Prachi
sir.
Verma is there. Yeah.
Yes, sir.
Prachi, you can start with your presentation.
Okay, sir.
Next presentation will be by Mitisha Bad,
So,
followed by Sandeep Kumar. Yeah.
something technical issue.
No. Yes, Prachi, you can continue, no problem. Mitisha, you can get ready, followed by Sandeep Kumar. You get ready with your presentation on. Okay, Prachi, you can share your screen.
Yes, sir.
Prachi, is there any problem?
So, हो नहीं पा रहा. Yes,
हो
sir.
नहीं पा रहा है. You go to share screen.
Yes, sir.
नीचे ग्रीन कलर का शेयर
सर
स्क्रीन दिख रहा है आपको?
लेकिन ये yes, sir.
Go to share screen. Then click on the screen and then click on the share.
Yes, sir. मेरा
You will have to take help of somebody who knows how to work with Zoom. Do you have somebody with you? Okay, Shikha Mitra is there. Sorry, Shikha Mishra. Shikha Mishra is there.
Hello. Yes, sir. Hello, sir.
Yes. Prachi, are you able to share your screen? Or you can try after some time.
Hello.
Hello.
Yes, sir.
Prachi,
Shikha Mishra.
yeah. Prachi, Can you share your screen, or we will try for after some time? Okay, Shikha, you can start.
Okay, thank you, sir. Hello,
Thank you,
everyone.
sir.
Good afternoon to all respected sir and ma'am. Myself, Shikha Mishra. I am PhD scholar from Dr. C.V. Raman University, Bilaspur. My topic is photoluminescence.
Shikha, you have to share your screen first.
Shikha, kindly share your presentation. And if possible, switch on your video.
My topic is photoluminescence behavior of rare doped gene molybdate.
Shikha, your screen is not visible. Shikha, your screen is not visible. Go to share screen.
Yes, sir. Yes, sir.
Click on share screen and then
Yes,
share
sir.
the screen. Your screen is not visible at all.
हाथ धोने की भी हिम्मत नहीं हो रही। अरे सुबह सुबह तो सैनिटाइजर सुबह हाँ ब्रश करने के लिए तो एकदम आइस कर 8 हो गया टेम्परेचर।
Sir, audible my?
Everyone,
You are audible, but your screen is not visible.
Hello?
Your screen is not
Okay,
visible.
sir.
सुनीता किधर है? केक बना रही है क्या? अच्छा वो काम कर रही होगी।
नहीं वो काम कर रही है।
इसका तुम लोग ना
Sir, visible my slide, sir?
No.
Hello?
No, it is not visible. No, it is not visible.
सर नेटवर्क इशू हो रहा है सर, दिख नहीं रहा है इसमें, हम तो शेयर कर रहे हैं इसमें।
नहीं, हमें नहीं दिख रहा है वो स्क्रीन। It is showing that it is you have started screen sharing, but the screen is not visible.
प्रोफेसर जुगाड़ी नेक्स्ट को ले लीजिए जब तक प्रॉब्लम अगर इनको हो रही है मैडम को शिप्रा मैडम को।
एक्चुअली हमने 3-4 पहले ही शिफ्ट कर दिए हैं
पहले ही शिफ्ट
फिर भी
कर
देखते
दिया
हैं।
है।
लेट अस सी। या यस, नेक्स्ट इज मितिशा।
यस मैम। यस मैम।
अच्छा यस, नाउ इट इज विजिबल।
प्राची?
नो
no
still it is not visible.
No, not visible.
Not visible.
It is not visible. Yes, something has appeared now.
Yes, something appeared. Hey. Yes, something appeared.
Now you can start your presentation.
Start.
पहले से ओपन करना चाहिए था।
स्लाइड नहीं दिख रहा मैम।
Just PDF भेजिए मुझे, ऐसे ही दिखेगा।
हेलो।
Good afternoon all of you.
You can open your presentation. Your presentation is still not
Presentation
visible.
open ही नहीं हुआ है।
Good afternoon all of you. Myself Prachi Verma.
Presentation.
Characterization of
Prachi, hold on.
प्राची प्रेजेंटेशन शेयर ही नहीं हुआ है आपका।
अभी हुआ।
Make it full screen.
Now you can start.
Thank you, sir. Good afternoon, all of you. Myself, Prachi Verma. Here I presented my recent work, synthesis and characterization of zinc oxide based nanocomposite. Next. These are contained. Next. I have introduced to what is nanotechnology. Nanotechnology is the science of small structure that generally measure less than 100 nanometer, in which 1 nanometer is billion of a meter. In 1974, Professor Nuru Taniguchi was first to introduce the multidiscipline covering research and technology from physics, biology, and chemistry. Almost all electronic devices made in the last decade use some technology, including today's more advanced computer chips, mobile phones, etc. Now, next. Now, introduce to brief knowledge of zinc oxide nanomaterial. It is an inorganic compound known as calamine flower of zinc. Zinc oxide exists of there are three types of crystalline structure: rock salt, zinc blende, woodside form. In this woodside form is more stable under ambient condition. Its multiple application is based on their physical and chemical properties. Nanostructure of metal oxide have been great attention in the field of nanotechnology, like zinc oxide, titanium oxide, tungsten oxide, etc. Next. Methodology. These are various types of methods are here, but I will explain our Sol-Gel method. It is an economical and low temperature and wet chemical technique, and method is used for the fabrication of metal oxide and conversion of monomer into colloidal solution that act as a precursor for gel. It is various step process are here. Hydrolysis, polycondensation, gelation, aging, drying, gasification, then last crystallization, further characterization. And now I will discuss I have used Sol-Gel method for synthesis of zinc oxide based nanocomposite, and I have मैम methodology में ही रहने दीजिएगा. I have synthesis zinc oxide nanoparticle and zinc oxide zinc oxide based nanocomposite via plant extract, in which plant extract is acting as a capping agent, and further synthesis nanomaterial used to characterization technique. Many characterization techniques such as UV analysis. Next. UV analysis. It is used to determine analyte concentration or chemical conversion of a component in solution, and it measures the absorption of light across the desired optical sample. And zinc oxide and zinc oxide based nanocomposite UV range is observed 369 and 430 nanometer, and zinc oxide based nanocomposite UV range 344 and 444 nanometer observed. Then FTIR analysis. FTIR spectroscopy. Generally, it is a technique measure the absorption of infrared radiation by the sample material versus wavelength. The infrared absorption band identify molecular component and structures. In this FTIR spectra, source peak at 3500 to 3000 centimeter inverse. It is generally source free hydroxyl in molecule, and OH group forming hydrogen bonds, and 1625 centimeter inverse stretching frequency and 698 stretching frequency is both that present in carbonyl and CH stretching vibration. Then next, Next conclusion, I send the nanomaterial for other characterization and further I will go for the application process. Thank you.
Okay, questions please, Patra sir.
Hello. Prachi, you go to your
Yes,
last
sir.
slide, conclusion. Last slide you have written
Yes, sir.
ice-handed. What means ice-handed?
Oh, sorry, sir. I have corrected.
No problem. So you have used zinc oxide. Why not the copper oxide nanoparticle?
Yes, sir.
Why you have chosen
Yes,
zinc
sir.
oxide? Why you have chosen zinc
Sir,
oxide nanocomposite?
it is a low cost and non-toxic nanomaterial.
Acha. And I have seen in your side that what is the difference between the nanoscience and nanotechnology?
Sir, it is a part of nanoscience. It is a part of nanotechnology. Sorry, sir.
अच्छा ठीक अच्छा बोलो तो you have used some a capping agent. What are the function of the capping agent?
Yes, sir.
क्या function है उसका?
सर वो सर
ठीक है next sir please.
Okay, Dr. Tangde.
Yes, Prachi, what are the application of your nanocomposites?
Sir, many types of application like photo degradation of dye and water treatment, wastewater treatment, and adsorption technique.
So, did you perform or are you planning for its application into one of the?
सर अभी मतलब प्रोसेस में है सर वो एप्लीकेशन.
Okay, what is your planning? I mean, where you are planning to use it?
सर हाँ सर फोटो कैटालिटिक डिग्रेडेशन के लिए और फोटो कैटालिटिक डिग्रेडेशन.
Thank you, Chairman sir.
Okay, the next presenter is Shikha Mishra. Swati, Prachi, you stop presenting so that Shikha can start her presentation.
Yes, sir.
Prachi,
Hello, sir.
you first stop sharing. Yes, Shikha, you can start presenting.
Yes, sir. Thank you, sir. Hello, everyone. Good afternoon to all respected sir and ma'am. Myself, Shikha Mishra.
Shikha, you first share your screen.
Yes, ma'am.
No, it is not still visible. I mean.
Sir, is it visible?
No, not yet.
It is visible from my side because.
Okay, there may be some bandwidth issue.
Yeah, I will share again.
Yeah.
Sir, is it now?
No.
No, ma'am.
Open your presentation.
Sir, it's open. Previous one was
We can see only your browser screen.
No, I'm on slide presentation.
Go to your presentation.
Might be there is some problem. Might be there is some problem because
no, you have to share your full screen. Maybe you are sharing only browser screen. Share it as a full screen.
Yes, sir. I'm sharing as a full screen. Is it visible?
No.
Because from my side, it is completely full screen visible.
No, when you click share screen, there are several options.
Yes.
So I guess you have selected this particular browser window to share. Share it as a complete screen. I mean, whatever you do on your screen that should be shared. This is what is the option. Try that option.
Now?
No, the same window.
Same as before. Same as before.
I don't know what is the problem with, because the previous one, the practice one is properly running.
Once again, you
That's why I'm
close
doing.
your presentation and open it again.
Reopen,
Okay.
yes.
I'm doing again. Is it visible now?
Yeah, yes.
Yes, now
Yes,
visible.
yes.
Thank you so much.
Ma'am, next slide.
Yeah. Okay, we can start.
Okay. My topic is photoluminescence behavior of rare earth doped zinc molybdate using reduced graphene oxide nanocomposites. Highlight of my work. First, the zinc molybdate doped European structure study depicts that the phase transition from monoclinic to trickling structure observed on heating as prepared sample at 400 and 600 Celsius. And second, the red photoluminescence intensity for the hybrid composites of zinc molybdate co-doped europium and lithium and graphene oxide or reduced graphene oxide is remarkably high. And third, the present sample would be useful for electroluminescence and photocatalytic applications. Ma'am, next slide.
Yes.
Figure 1 represents the XRD spectra of as a synthesized GeMel, and zinc molybdate doped europium and using graphene oxide or reduced graphene oxide. All samples annealed at 400 Celsius and 600 Celsius. The XRD spectra show a remarkable shift
2 मिनट पढ़ लें,
in
2 मिनट
position and intensity of the diffraction peaks. The respective change in XRD spectra attributed to the phase transformation of as prepared samples during the annealing process. The crystalline size of zinc molybdate co-doped europium and lithium sample prepared by solvothermal and polyol has been estimated as approximately 71 nanometer and 59 nanometer. Ma'am, next slide. Ma'am, next figure 2 listed the XRD spectra of graphene oxide and reduced graphene oxide powder. The XRD peaks observed for graphene oxide at 30.1 degree and 42.48 degree represents 001 and 100 reflectance planes respectively. Similarly, reduced graphene oxide exhibits peak at 24.66 degree and 42.76 degree owing to the 002 and 100 reflectance planes respectively. Figure 2b illustrate the Raman spectra of zinc molybdate uh, doping europium and graphene oxide and reduced graphene oxide samples. The spectra consist of peaks at 119, 181, 327, 814, 852, and 915 per centimeter. The band at 190 and 181 per centimeter O the symmetric stretch of the zinc to oxide bonds, and subsequently the peak and 327 per centimeter attribute to the strength zinc oxide of the distorted attachment zinc oxide octahedral cluster in a chain. Additionally, the peak at 814 and 852 per centimeter correspond to the antisymmetric strength oxygen molybdate oxygen bond, while the peak at 950 per centimeter attribute to the symmetry stress oxygen molybdate and oxygen bonds, the tetrahedral molybdate cluster. And next. Next, ma'am. Figure 3 show the scanning electron micrograph of the as a synthesized sample. It shows that the zinc molybdate doping europium has particles of a cuboid shape with a average size approximately 1 to micrometer. The particle size increases on heating samples at 400 Celsius and 600 Celsius to approximately 2-3 micrometer. Next. And figure 4 depicts the diffuse reflectance spectra of as a prepared annealing sample zinc molybdate doping europium and co-doped europium and lithium. It is evident from the DRS spectra that zinc molybdate doping europium exhibit a broad absorption band in the range 320 and 350 nanometer. However, the absorption wavelength gets slightly changed for the lithium co-doped zinc molybdate europium and lies in the range 320 to 360 nanometer. The absorption band show a red shift after heating the sample at 400 Celsius and 600 Celsius. The minimum transformation has been found at 360 and 370 nanometer respectively for the sample. And the next figure 5 PL emission spectra of as a prepared annealed 400 and 600 Celsius at excitation wavelength 266 nanometer. And first figure of zinc molybdate and 2% europium. And next B zinc molybdate is co-doped 2% europium and 5% lithium. Inside PL emission spectra of zinc molybdate, co-doped europium and lithium synthesized by solvothermal and polyolthermal. And figure C, sample hidden in oxygen atmosphere. Ma'am, next. And next CI diagram has been plotted in figure. The CI coordinate of zinc molybdate europium co-doped europium and lithium and 600 Celsius are all composites are 0.64, 0.36 and 0.66 and 0.34 and 0.66, 0.34 and respectively. These ordinate are near to standard anti-SC red coordinate. Therefore, graphene oxide or reduced graphene oxide can be potential red emitter and can be used in field emission display. And last, my conclusion. Summarily, the sample have been successfully synthesized by adopting a facial and simple solvothermal method. The XRD spectra illustrate the occurrence of phase transition from monoclinic and twinkling phase in zinc molybdate after annealing at 400 to 600 Celsius. The Raman spectra display the vibration modes of molybdate group in addition to D band and G band of graphene oxide or reduced graphene oxide sheet. The optical measurements have been performed by DRS spectra and photoluminescence emission spectra. The DRS spectra exhibit that the sample show red shift in absorption after annealing the sample at 400 to 600 Celsius. Moreover, PL down conversion spectra of zinc molybdate doping europium using graphene oxide and reduced graphene oxide hybrid nanocomposites display characteristic emission peaks of europium ion and zinc molybdate doped europium using reduced graphene oxide sample possess higher PL intensity as compared to zinc molybdate doped europium using graphene oxide samples. Hence, fourth, the study hybrid nanocomposite may be used as a potential phosphor in the field emission display device. Okay, thank you, sir. Thank you, ma'am.
Thank you, Shikha.
Okay, thank you, sir.
Just I have some queries that do you know that nowadays the naming as the rare earth is misnomers. We cannot use the name as rare earth now because some elements are there, they are more rare than the rare earth. Achha. And why that the rare earths, they are having some good photoluminescent property? Do you understand?
Shikha, have you understood the question? Shikha, have you understood the question?
Shikha? I think connection is lost.
I think so.
Okay, sir. Next.
Okay, in that case, we'll move ahead to the next one. Next one is Mitisha Baid. Mitisha Baid, are you there? Mitisha? Okay, next one is Sandeep Kumar. Sandeep Kumar is there?
Yes, sir.
Yeah, Sandeep Kumar, you can start your presentation.
Okay, sir.
If you are working with two different devices, then there will be echo like this. Yes, Sandeep Kumar, share your screen.
Yes, sir.
Yes. You can start
You
your
are visible, yes.
Good afternoon, sir. Myself, Sandeep Kumar. I am research scholar under the supervision of Dr. Alka ma'am. And my topic is removal of anionic diacid blue 25 by adsorption method. And these are my content for related my work. And first is the introduction. We know that the chitosan is the natural polymer derived from the chitin, and the chitin is the second most abundant biopolymer after the cellulose. And our main work is to develop some low-cost, eco-friendly adsorbent from the chitosan, and to assess the potential of grafted matrix for the removal of toxic dye for aqueous medium. And this is the structure of chitin derived from the marine endoskeleton of marine animal scrap. And this is the structure of chitosan derived from the chitin by deacylation process. And the next is the modification of chitosan. Chitosan having some drawbacks like low solubility, biodegradability, and a low tensile strength and less thermal stability. So enhance its property to modify the chitosan backbone by grafting or the cross-linking method. Grafting is a process by which two different plant polymer are united so that the product has additive property of both. And grafting is an attractive technique to modify natural chitosan, which is carried out through free radicals that are carried by radiation or chemicals. Here, effect on radiation effect on organic material. For the grafting, I have used gamma radiation, and the gamma radiation produced from the cobalt-60 isotope. When the gamma radiation strike on the sample or chitosan, the free radical are generated on the surface of chitosan, and this chitosan are interact to vinylic monomer free radical by radical interaction. And this is the simply showing the grafting on plant and chitosan backbone. And by grafting, the desired functional group can be introduced onto the surface of chitosan backbone. And this is the base polymer of chitosan, and grafting to desired material on the surface of chitosan. And adsorptions of dye. This grafted sample are used as an adsorbent for the removal of toxic dye. And this is the structure of chitosan, and this is the structure of vinylic monomer like METC, and this is the structure of chitosan grafted METC. And here the chitosan grafted METC is the adsorbent, is a cationic adsorbent, and it is used for the removal of some dye, for the monoanionic dye, polyanionic dye, and dianionic dye. And I have removed acid blue 25 using chitosan grafted METC. And there are some effects on the removal of factor affecting the removal of acid blue 25. First is the effect of concentration on the percentage removal of acid blue 25. Second is the effect of time on the percentage removal of acid blue 25. And next is the effect of adsorbent dose. And next is the effect of pH. Here the 93% removal of acid blue 25 in 30 ppm concentration of dye solution, and 3 hours and 0.5 gram of adsorbent at neutral pH. And there is adsorption isotherm. Here equation 1 is the Langmuir adsorption isotherm, and equation 2 is the Freundlich adsorption isotherm. And figure 5 is the Langmuir adsorption isotherm for dye solution acid blue 25 at 30 ppm solution. And figure 6 is the Freundlich adsorption isotherm for dye adsorption acid blue 25. And here the R square value is 0.9979 for the Freundlich adsorption isotherm. That means the adsorptions of acid blue 25 is followed by Langmuir adsorption isotherm, and Qmax means maximum adsorption capacity is the 5.25 milligram per gram. Here the kinetic of acid blue 25, equation 3 is the pseudo first order kinetics, and equation 4 is the pseudo second order kinetics. Here figure 7 is a pseudo first order plot for the adsorptions of dye acid blue 25, and figure 8 is the pseudo second order plot for the adsorption of acid blue 25 at 30 ppm concentration of dye solution. Here the R square value is high for the pseudo second order plot is 0.9989. That means the removal of acid blue 25 follows second order kinetics. And conclude of my work here, the conclude my work is the chitosan grafted METC is highly effective for the removal of acid blue 25 and the removal of reactive red 120 and the removal of reactive orange 16 dyes. And there are some references, and our first research paper published on related of my work in RPC Journal. Thank you.
Thank you, Sandeep, for your nice presentation.
Thank you, sir.
I have few queries that for grafting of the chitosan, you use that gamma radiation, na?
Yes, sir.
And where from do you do this? कहाँ से करते हैं?
सर इसके लिए मैंने भाभा एटॉमिक रिसर्च सेंटर मुंबई में वर्क किया है, और वहाँ जाके मैंने ये पूरा सैंपल सिंथेसाइज किया है। एडसॉर्प्शन हमने एडसॉर्बेंट हमने वहाँ बनाया है सर, भाभा एटॉमिक रिसर्च सेंटर मुंबई।
अच्छा, बहुत अच्छा। नेक्स्ट है वो जो आपको जो डाई रिमूवल होता है चिटोसान से, एक मतलब कितना परसेंटेज तक होता है? हाउ मच परसेंटेज ओवरऑल?
सर काइटोसन से तो कम होता है सर ये परसेंटेज रिमूवल 70 to 72%। तो हमने फिर सर इसको मॉडिफाई किया हुआ है इसमें विनाइलिक मोनोमर लेके। तो सर ये जो परसेंटेज रिमूवल है इसका 93 to 95% रिमूवल है सर।
अच्छा, ठीक ठीक, थैंक यू। नेक्स्ट प्लीज।
थैंक यू सर।
Sandeep,
yes sir,
how did you calculate Qmax?
Sir, Qmax, sir, I have used this log Q equal to log Kf.
Yes, that is the standard relation of Freundlich adsorption isotherm. It is fitting well. I mean, we can see here. But then yes, Qmax, how did you reach to the conclusion that this is Qmax? Because you need some other other values, parameters to calculate. This formula doesn't give you Qmax.
Yes, sir. Sir, there are many type of formula for the calculating of Qmax.
I mean, based on Freundlich adsorption isotherm, did you calculate Qmax?
Yes, sir.
Okay, I just wanted to know how did you calculate. Then the second thing, did you compare your results with the literature?
Yes, sir. I have also compared this literature, and this chitosan grafted METC is highly effective for the removal of acid blue 25.
Yeah, because currently the chairman of the session is having extensive work in this field. So he will better will be speaking. The other part is, did you see the intraparticle diffusion? I mean, the
No, sir.
kinetic studies through intraparticle diffusion.
No, sir.
Because second order, it is fitting well. So I was looking for whether you have studied for intraparticle diffusion or not.
No,
The
sir.
Lagrangian doesn't fit, it seems. Anyway, thank you. Over to chairman, sir.
Yeah, Sandeep, interesting work, and it is the work of my interest. So definitely I have some questions. As far as the work of gamma irradiation is concerned, I want to inform you that our department of chemistry is having a cobalt 60 source. And if you want any assistance from my side, definitely you can send your samples for gamma irradiation. And if you want to carry out some grafting, etc., by physically coming to our department, definitely you can come at any time, and we extend our facilities to you.
Thank you,
sir. That is one thing. Second thing, which is more actually a problem for me, is you are carrying out grafting, and after grafting, you must characterize your material. I haven't seen any characterization after grafting. You should have a comparison of chitosan with grafted chitosan.
Sir, I have also characterized this grafted sample, and I have published one research paper in radiation physics and chemistry, sir. And
yeah, it's one of the very good journals for radiation effects.
Yes, sir.
But the question I have is, if you are using gamma irradiation, gamma is so high energy radiation that it does not discriminate between the bonds and bonds. So one side it will graft chitosan, and at the same time it can actually break down chitosan. So both the things can take place because gamma is not a selective radiation. So that's why my question is whether at that time the chitosan moiety is preserved or it is degraded. That is a question. What is the dose you have used? Are you getting my question?
Sir,
Sandeep?
सर हाई डोज में सर काइटोसन तो डिग्रेड हो जाता है, लेकिन सर हमने काइटोसन को सबसे पहले क्रॉस लिंक किया हुआ है और उसके बाद हमने इसको ग्राफ्ट किया हुआ है.
Yes, but what is the dose? How much dose did you give?
So for the cross linking, sir, I have given the dose is 50 kilogray, and for the grafting 8 kilogray only for the grafting of METC.
Okay, at that dose there is no degradation. Are you sure?
No, sir, no degradation.
Okay, okay, we can have some discussion afterwards also. Okay, thank you.
Thank you.
Next presentation is by Anjali Verma. Yeah, Anjali, you can start your presentation.
Not visible.
Anjali, your presentation is not visible.
Yes. Sir, visible?
No. Yeah, it is visible now. You can go ahead.
Sir, मेरे तरफ visible नहीं हो रहा.
You can again start sharing. Yes, now it is visible. You can go ahead.
Yes, sir. I'm Anjali. I'm a research scholar under the supervision of Dr. My
Voice is not clear. Please make it. Your voice is not clear.
No, voice is not clear, Anjali. No, it's not very clear. It is cracking in between. Anjali, are you there? Okay, we'll move to the next one. Yeah, Anjali. Next, Tulika is there. Tulika Devangan.
Yes, Anjali started
Okay.
sharing a screen.
Yeah, Anjali.
Please pick out something. Anjali, you are not audible. Anjali, we can see your slides, but you are not audible.
You are not audible, Anjali.
There is a network issue, I think, from her end.
Anjali,
Anjali, you
unmute
can go
yourself.
to. Yeah,
Unmute
Anjali,
yourself.
unmute yourself.
Anjali, please check whether you are muted yourself.
Yes, sir, she is muted. I'm calling her.
Yeah.
Good afternoon, sir. Sir, voice आ रही है?
हाँ, आ रही है.
अभी आ रहा है.
Yes, sir, yes. Good afternoon, sir. Good afternoon to all of you. Myself, Anjali. These are my topics: synthesis and characterization of the coastal silk fiber by grafting. These are contained. Introduction. Chhattisgarh state is the biggest producer of the finest coastal silk. The word coastal derived from the Sanskrit word meaning silk. The silk is created by small silkworms when they feed on mulberry fruit and produce a kind of fine silk. These coastal fibers are drawn from the cocoon of silkworm known as Centria mylitta, found in Saja, Arjun, and salt trees. Each cocoon of coastal silkworm yield 1 to 2 grams of silk yarn, equivalent to about 300 yards of the thread. Silk fiber. Silk consists mainly two types of protein. First is sericin and second is fabrion. Silk fiber consists of 70 to 80% of fabrion and 20 to 30% of sericin. Fabrion being the structural part of silk fiber and sericin being the gum coating the silk fiber and allowing them to stick to each other. Fabrion is made of the amino acids like glycine, sericin, glycine, alanine, and form beta-plated sheets. And these are the chemical composition of silk fiber. Next is synthesis of coastal silk. The process of synthesis of coastal silk are following steps. First is cocoon cultivation, second is thread making, third is weaving, and fourth is printing or embroidery. Properties of coastal silk fiber. Coastal silk fiber has a great recognition of its softness and elegance, and therefore it is extensively used for making different Indian traditional garments. The advantage of coastal silk fiber are it is highly resistant to deformation, good insulation property, good affinity to dye, steamer and shine, and non-toxic to biodegradable. But there are some also drawbacks of silk fiber. like it gets highly crushed and damaged by sun and water explosion, and so less resistant. So improve its drawback, we need to modify the silk fiber. So the modification of silk fiber is grafting method, and second is cross-linking method. In grafting method, grafting is an attractive technique to modify natural silk fiber, which is carried out through particles that are created by radiation chemicals. By grafting, the desired functional group can be introduced onto silk fiber backbone, and mechanical and physiochemical property can be improved. Next is grafting method. Grafting method has generally two types. First is chemical grafting and second is radiation grafting. In chemical grafting, silk fiber can be modified by chemical method in which the use of monomer, cross-linker and initiator is required. And radiation grafting, grafting initiated by radiation technique, is known as radiation-induced grafting. My work is related to synthesis of kosa silk fiber by using chemical grafting. So these are the mechanism of chemical grafting. In this mechanism, firstly silk fiber backbone reacts with free radical initiator, and then free radical sites form the free radical sites of silk fiber backbone, and then added to vinyl monomer, and finally silk fiber will be formed. Next is synthesis and characterization of silk fiber. I have synthesized silk fiber with using vinyl monomer like vinyl benzyl trimethyl ammonium chloride and 2-acryloxide ethyl trimethyl ammonium chloride. And I have optimized its different conditions like initiation time, initiation concentration, catalyst concentration, monomer concentration to make the graft copolymerization more efficient. And the fiber will get the FTI A pure fiber, B grafted silk fiber, and C grafted silk fiber. FTI respect of silk is strong when above 3,000 inwards is due to OS and NS stretching frequency and stretching vibration, and 1700 to 600 centimeter inwards, which are indicated polypeptide and protein vibration. FTI spectra of VBT grafted silk fiber shown in figure, the peak at 2400 to 2251 centimeter inwards due to quaternary ammonium, 1600 centimeter inwards due to aromatic ring, and 2900 centimeter inwards due to CH stretching. In the magnetic grafted silk fiber, when due to the introducing on trialkyl amino, in a silk was clearly indicated by a band range 2372 to 2277 centimeter inwards and 1483 centimeter inwards, and carbonyl graph at 1632 centimeter inwards. These are references. Thank you.
Nice presentation.
Thank you.
Just how the composition of that kosa silk can be determined? The composition of kosa silk, how you get?
Yes.
आपको कैसे पता हुआ उसमें क्या क्या है?
सर मैंने
आपका आवाज ठीक से नहीं आ रहा है, काट रहा है. Have you made any comparison with some other silk?
No, sir.
ठीक है. Sir, next. Sir.
Yes. Anjali, are you reporting this chemical grafting for the first time?
Yes.
I mean, did you check whether in the literature other grafting methods or say similar grafting methods are available?
Yes, sir.
So, is it available? You are not audible.
Hello.
Hello. Ha. So, if it is available in the literature, did you compare?
Yes, sir.
So, I could not see the comparison. The other thing is the description of IR spectra that you have given. I mean, the peaks you were describing were not matching with what you were showing. I mean, I was a little bit confused while the discussion, I mean, what you were discussing in the IR spectra. Is it the same IR spectra that you were describing? Like I could not see the peak at 2900 you were describing. Anyway, over to Chairman, sir. Thank you.
Okay. Next presentation will be by Tulika Devangan. Tulika, are you there? Tulika? Anjali, you stop sharing so that next presenter can, yeah. Anjali, you stop sharing so that next presenter can share. Tulika, are you there? If Tulika is not there, then Nurafsha.
Yes,
Nurafsha?
sir.
Yeah.
Yes, sir.
Nurafsha, you can start presenting.
Okay, sir.
Yes, you can go ahead.
Okay, sir. Good afternoon to all of you. Myself, Nurafsha, and I presented my paper in green synthesis of copper oxide nanoparticles from Nictanthus arboricolis leaf extract and its antibacterial activity under the supervision of Dr. Anil Kumar Kashyap. These are the contents. First is introduction. In this study, copper oxide was synthesized. Copper oxide nanoparticle was synthesized using a copper sulfate pentahydrate precursor, and I choose Nictanthus arboricolis leaf extract as a reducing and capping agent during the synthesis. And this plant is also known as a Shringhar. As we know, the indispensable microelements obligatory for the growth and development of plant. It can be present as a copper ion, 2+ ion and copper ion under natural conditions. However, a higher dose of copper leads to oxidative stress generation, growth inhibition, cellular malfunctioning, and photosynthesis retardation. Nictanthus arboricolis is a medicinally important plant of family Oleaceae and exhibits pharmacological activities like antioxidant, anti-helminthic, antiviral, anti-leishmania, anti-allergic. Methodology: I take fresh leaves of healthy plants and washed several times, and by drying and grinding, and boiling of 10 gram of leaf powder in 100 ml of distilled water. Then after filtration, leaf extract. Now, green synthesis of copper oxide nanoparticles. In this, I prepare 3 different concentration of copper sulfate, that is of 2 mm, 5 mm, and 10 mm. In 90 ml of metal solution, 10 ml of leaf aqueous extract was added dropwise under stirring. As soon as the leaf extract comes in contact copper ions, spontaneous change, the blue color of the copper ions turns to the green color, and the obtained green mixture was left under stirring at room temperature. After 2 hours, the green mixture was started changing to brown suspended mixture, indicating the formation of water-soluble monodisperse copper oxide nanoparticles. After and by XRD, the characterization confirmed that the biosynthesized copper oxide nanoparticles resist as a good crystalline nature, which perfectly match the. These are the FTIR of leaf extract, and comparatively with the copper oxide nanoparticle, FTI spectra of the copper oxide nanoparticle showed a strong and sharp peak at 506 to 603, that is 530 to 597 range, peak in the range of 600 copper oxide, and the absorption peak appearing at 1584, and 3254 of copper oxide could be correlated to the bending and stretching vibration of adsorbed water and surface hydroxyl group. These are the SAM images of my sample 1, sample 2, sample 3, that is of 2 mm, 5 mm, and 10 mm solution. It is clearly observed that in sample 1, it is cobodial shape, and that second one is of agglomerated spherical shape, and third is of spherical shape. These are the antibacterial activity I have done. At 3 different concentration, that is of 2.5 microgram, 5 and 8 microgram. Comparatively, in between gram positive and gram negative bacteria, it shows that the Staphylococcus E. coli is very sensitive. The opposite charges that gram negative easily kill by the copper oxide nanoparticle. The opposite charges that exist on the bacterial chains and copper ions released from the nanoparticles are thought to cause addition and enhance bioactivity due to the electrostatic forces. As a result, some peptidoglycans as negatively charged molecules, they bind with the copper ions released from copper oxide nanoparticles in a liquid growth medium. And nanoparticle may attach to the negatively charged bacterial cell wall and rupture it, leading to the protein denaturation and cause cell death. These are the findings. This finding of this study also revealed that the gram positive bacterial strain were less sensitive negative of copper oxide nanoparticles. Thank you.
Thank you, Nurab sir, for a nice presentation.
Thank you.
Just a few queries that you have tested your antibacterial activity with some known antibiotic.
Yes, sir, chloramphenicol.
Achha. And
As a positive control, I have done.
The effectivity is how much? It is more than that or less than?
More than that, sir. As in graph, I will show that positive control PC is, so zone of inhibition is 12 and 9 for
Next
F. and E. coli.
You have told something that they have some anti-leishmanial activity also, na?
Yes, sir.
So do you know that सबसे ज़्यादा anti-leishmanial activity किसका है? Most anti-leishmanial activity?
Sorry, sir.
And who discovered that? An Indian scientist. He is very famous. And few days back, I think he has some birth anniversary. UN Brahmachari.
No, sir.
Thank you. Thank
you. Okay.
Noor Afsha, it was a nice presentation. Can you go to that IR slide wherein you have shown the IR of that leaf extract?
IR. This one?
Yes. So if you look at the copper nanoparticle IR and the leaf extract, the IR seems to be very clear. I mean, comparatively, this of copper oxide nanoparticles. I mean, I'm surprised to see such a clear IR of leaf extract.
Yes, sir.
Can you explain?
Sir, as in leaf extract 3421. Sorry.
Did you isolate it?
Sir, as 3326.74 is for alkene CH group, and
yes, but then there must be some other groups as well because it is a natural compound.
Yes, sir.
But so such a clear IR, I'm surprised to see.
Sir, I can't understand the question.
I mean, why other groups are not seen in IR? I just would like to know because it is a natural extract, na?
Sir, a lot of functional groups present.
Yes, but I cannot see in IR the other functional groups.
Yes, sir.
So such a clear, I mean, it is like separated or isolated functional groups like IR is shown over
sir,
here. whereas you have shown particularly good copper oxide nanoparticle IR.
Yes, sir. In which the intense peak shows us that only that much I present.
Okay, is it a PhD work or it is a MSc dissertation work?
Yes, sir. It's PhD.
Okay. Thank you.
No,
Over
sir,
to Chairman,
it's
sir.
PhD.
Yeah. Okay. Thank you very much, Anurag sir. There are a few participants who were missing. Is Dr. Shweta Kumbhaj is there? Then Dr. Sarabjot Kaur, Sachin Shende, then Mitisha Baid, and Tulika Devangan. So these 5 participants were not there, and 7 participants, they presented their work nicely. So congratulations to all of you for your participation in the oral presentation. Thank you very much to the jury members, Dr. V.M. Tangre and Dr. Gautam Kumar Patra sir. Thank you.
Thank you,
very
sir.
much.
Thank you.
Thank you, sir.
Yeah.
Thank you, all of you, sir. So I think tomorrow we will meet at 11 a.m. Tomorrow there will be 3 talks. One is Professor Ramaswara Adhikari from Nepal, and there is Dr. Ashish from Central Center for Display Technology, IIT Kanpur, and third one is Dr. Sunita from Surajpur, Chhattisgarh. After that, there is a presentation of the students, and chairman is, I think, Dr. Joshi, Tejas Joshi from Bhavnagar University. So thank you, Professor Praveen Jugade sir, Dr. Vijay Tangre sir, and Professor G.K. Patra sir for
Thank you, sir.
your support and cooperation.
Thank you, sir.
We will meet in future. Thank you, sir.
Thank you.
Thank you. Thank you, sir.
Thank you.
Thank you, sir.
Shall we end the meeting, sir?